Welcome, we're so happy you tuned in tonight. Before we get started, I'd love to know, where are you watching from? Drop it in the comments. Now, let's get comfortable and drift into deep, peaceful sleep together. The sun is a star at the centre of our solar system. It sits there, quiet and enormous, anchoring everything around it with gravity and light. When you think about the sun, you might picture something fierce or blinding, but tonight we're going to think about it differently. Tonight the sun is just a steady presence, a kind of cosmic hearth that has been burning gently for longer than anything you can imagine. There's no urgency here, no need to hold on to these facts too tightly. They're just here to keep you company as your mind begins to settle, as your breathing slows, and as the day finally releases its hold on you. The sun is a huge sphere of hot gas, mostly hydrogen and helium. That's all it is, really. Gas, held together by its own gravity, compressed and heated until it glows. There's something calming about that simplicity. No solid ground, no surface you could stand on, just layers of gas pressing inward, getting hotter and denser the deeper you go. The sun contains most of the solar system's total mass. When scientists add up everything in our neighbourhood of space, all the planets, all the moons, all the asteroids and comets and dust, the sun accounts for more than 99% of it all. Everything else, including Earth, is just a collection of leftovers, small fragments that didn't fall into the sun when the solar system was forming. The sun's gravity holds the planets in their orbits. That invisible pull reaches out across millions and billions of miles, keeping Earth on its steady path year after year, century after century. We orbit because the sun is there, massive and patient, never letting go. The sun looks constant, but it is always active in gentle ways. If you could watch it closely over hours or days, you'd see patterns shifting across its surface, bright regions and dark regions coming and going, loops of glowing gas rising and falling. But from here, from Earth, it just looks like a steady circle of light. That's okay. You don't need to see the details to feel the constancy. The sun's energy comes from nuclear fusion in its core. Deep inside, where the pressure is immense and the temperature climbs to millions of degrees, hydrogen atoms are squeezed together so tightly that they combine. Fusion combines hydrogen into helium. 4 hydrogen nuclei become 1 helium nucleus, and in that transformation, a tiny amount of mass is converted into energy. It's the same process that powers hydrogen bombs, but in the sun it happens in a controlled, sustained way, not as an explosion but as a continuous burn that has lasted for billions of years. Fusion releases energy as light and heat. That energy starts deep in the core, but it doesn't escape right away. It takes a long, slow journey outward, bouncing and scattering through the sun's inner layers, sometimes taking hundreds of thousands of years to work its way from the centre to the surface. By the time it reaches the surface and radiates out into space, it's the sunlight you know, the warmth on your skin, the brightness in the sky. The sun has been shining for billions of years, about 4.5 billion years to be more precise, though precision isn't really the point tonight. The point is just to know that the sun is old, ancient even, and that it has been doing this same steady work since long before there were people to notice it, long before there was anything alive on Earth at all. The sun is close compared with other stars, which is why it looks so large in our sky. The nearest star beyond the sun is more than 4 light years away, a distance so great that even travelling at the speed of the light, the fastest anything can go, it would take over 4 years to get there. The sun, by contrast, is only 8 light minutes away, close enough that its light reaches us in the time it takes to boil water or listen to a couple of songs. That closeness is what makes the sun special to us, what makes it the sun and not just another point of light. Just one more small fact, and then we drift. Sunlight takes time to travel to Earth. Even though light is fast, the fastest thing there is, it still needs time to cross the distance between the sun and our planet. That travel time is a little over 8 minutes, 8 minutes and 20 seconds if you want to be exact, though again, exactness can wait for another day. When you feel sunlight, you're receiving a message from minutes ago. The light that touches your face left the sun's surface 8 minutes earlier. In a way, you're always seeing the sun as it was, not as it is. It's a small delay, barely noticeable, but it's there. A reminder that even light has to travel, that even the fastest things take time. The sun's light spreads outward in all directions. It doesn't aim for Earth specifically. It just radiates, sending energy out in every direction equally, and Earth happens to be in the path of a tiny sliver of that outward flow. Earth receives only a small fraction of the sun's total output. If you imagine the sun's energy as a sphere expanding outward, Earth would intercept only about 1 part in 2 billion of it. Everything else flies off into space, warming nothing, lighting nothing, just travelling outward until it fades into the cold emptiness between stars. Even that small fraction is enough to power weather and life. Every gust of wind, every rainstorm, every growing plant, every breath you take, all of it traces back to that thin stream of sunlight falling on Earth's surface, day after day, year after year. Sunlight includes many wavelengths, not just visible light. When you see sunlight, you're seeing only a narrow band of the electromagnetic spectrum, the part your eyes happen to be sensitive to. But sunlight also carries wavelengths you can't see. Some sunlight is infrared, which we feel as warmth. You can't see infrared light, but you can feel it when you stand in the sun and your skin grows warmer. That warmth is just another form of light, vibrating at frequencies too slow for your eyes to detect. Some sunlight is ultraviolet, which Earth's atmosphere helps filter. Ultraviolet light carries more energy than visible light, enough to damage living cells if too much gets through, but the ozone layer high in the atmosphere absorbs most of it before it reaches the ground. What does get through is enough to tan your skin or, over time, cause sunburn, but it's a small fraction of what the sun actually emits. Daylight on Earth is a gentle result of rotation, not the sun turning on and off. The sun doesn't sleep. It doesn't dim at night. Night happens because Earth turns, rotating on its axis once every 24 hours, and as it turns, different parts of the planet face toward the sun or away from it. When your part of Earth turns away, the sun's light is blocked by the planet itself, and you experience night. When your part turns back toward the sun, light returns, and you have day. It's a slow, steady spin, one that's been going on for as long as Earth has existed, and it will keep going long after you've drifted off to sleep tonight. Just one more small fact, and then we drift. The sun has layers, like a deep, glowing onion of heat. If you could slice the sun open, not that you'd want to, not that you could, you'd see that it's not uniform all the way through. The core is where fusion happens. That's the centre, the hottest and densest part, where hydrogen becomes helium and energy is born. The core is small compared to the sun's total size, only about a quarter of the sun's radius, but it contains more than half of the sun's mass, all of it squeezed down by the weight of everything above it. Outside the core is the radiative zone. This is a thick shell of gas where energy from the core begins its slow journey outward. In the radiative zone, energy moves outward mainly by radiation. Photons of light are emitted, absorbed, re-emitted, absorbed again, bouncing around in a random walk that takes thousands or even hundreds of thousands of years to complete. It's not a straight path. It's a chaotic, wandering journey, each photon scattering off particles of gas, changing direction over and over, inching outward bit by bit. Beyond that is the convective zone. Here the gas is cooler and less dense than in the radiative zone, and energy starts to move in a different way. In the convective zone, hot material rises and cooler material sinks. It's like a pot of water simmering on a stove, where heat at the bottom causes the water to rise, and cooler water at the top sinks back down to take its place. This slow churning helps bring energy toward the surface. The convective zone is where the sun's internal heat starts to become something you could almost recognize, where the abstract energy of fusion becomes the motion of gas, rising and falling in great loops that span thousands of miles. The sun's visible surface is called the photosphere. This is the layer you see when you look at the sun, though you shouldn't look directly, of course. The photosphere is where the sun's gas becomes thin enough that light can escape into space. Below this, the gas is too dense, too opaque, and light just gets absorbed and re-emitted over and over. Above this, the gas is too thin to emit much light at all. The photosphere is the Goldilocks layer, the place where conditions are just right for light to break free and travel outward. Above the photosphere is the chromosphere. This is a thin layer of gas that glows faintly, usually only visible during a solar eclipse when the bright photosphere is blocked. The chromosphere is hotter than the photosphere, which seems strange. You'd expect the sun to get cooler as you move away from the core, but the reasons for this heating are still being studied. Farther out is the corona, the sun's outer atmosphere. The corona extends far into space, millions of miles out, fading gradually until it blends into the solar wind. The corona is also surprisingly hot, even hotter than the chromosphere, reaching temperatures of 1,000,000 degrees or more. How the corona gets so hot is one of the ongoing puzzles in solar physics, something scientists are still working to understand. But for now, tonight, you don't need to solve it. You just need to know it's there, a vast glowing halo surrounding the sun, invisible most of the time but always present. Just one more small fact, and then we drift. The sun's surface looks textured because of convection. If you could see the sun up close, if you had a telescope powerful enough and filters dark enough to protect your eyes, you'd notice that the surface isn't smooth. It looks grainy, covered in a shifting pattern of bright cells surrounded by darker lanes. Those bright grainy cells are called granules. Each granule is a region of rising hot gas. The gas rises because it's hotter and less dense than the gas around it, buoyed upward by convection. When it reaches the surface, it spreads out, cools slightly, and then sinks back down. The darker edges are where cooler gas sinks back down. It's a continuous cycle, each granule lasting only about 10 or 20 minutes before it breaks up and reforms. The pattern is always there, always changing, like the surface of a slowly simmering soup. This pattern is like slow simmering, not violent motion. It's easy to imagine the sun as a violent, explosive place, but most of what happens there is actually quite gradual. The gas moves, yes, but not at terrifying speeds. The granules rise and fall at a few hundred meters per second, which sounds fast until you remember how large the sun is. On a human scale, it would be like watching paint dry, or watching clouds drift across the sky. Gentle, inevitable, calm. The sun rotates, but not all parts rotate at the same speed. The sun isn't a solid object, so different parts of it can rotate at different rates. The equator rotates faster than the regions near the poles. At the equator, the sun completes one rotation in about 25 days. Near the poles, it takes closer to 35 days. This is called differential rotation, and it happens because the sun is made of gas and plasma, not rock or metal. There's no rigid surface to keep everything moving together. The sun's rotation helps shape its magnetic field. As the sun rotates, it drags its magnetic field along with it, twisting and stretching the field lines. The magnetic field is always changing and shifting. It's not a simple bar magnet, North Pole and South Pole, neat and symmetrical. It's a tangled, complex structure with loops and knots and regions where the field is strong and regions where it's weak. Much of the sun's activity is really magnetic patterns moving over time. Sunspots, flares, prominences, all of these are driven by the sun's magnetic field, by the way the field twists and reconnects and releases energy. Just one more small fact and then we drift. Sunspots are darker regions on the sun's surface. They're not actually dark. If you could see a sunspot on its own, it would glow brightly, hot enough to vaporize any material you can think of. But they look dark compared to the surrounding areas because they're cooler. They look dark because they are cooler than surrounding areas. A typical sunspot might have a temperature of around 3,500 degrees Celsius, while the rest of the photosphere is closer to 5,500 degrees. That difference is enough to make them stand out as dark patches against the bright background. Sunspots are linked to strong magnetic fields. Where the sun's magnetic field is particularly strong, it can inhibit the convection that normally brings heat to the surface. The result is a region that's slightly cooler and therefore slightly darker. Sunspots can appear alone or in groups. Sometimes you'll see just one or two small spots. Other times you'll see large, complex groups with dozens of spots clustered together, some of them larger than the entire Earth. Sunspots change over days and weeks. They grow, they shrink, they merge with other spots or split apart. They drift across the sun's surface as the sun rotates, appearing on one side, moving across the face of the sun, and then disappearing around the other side. If you watch the sun every day, you'd see them come and go, a slow parade of dark patches marching across the glowing disk. The sun can also have bright regions called faculae. These are areas where the magnetic field is strong, but the effect is different. Instead of cooling the surface, the field allows more heat to escape, making these regions brighter than their surroundings. Faculae are often easier to notice near the sun's edge. Near the center of the sun's disk, they don't stand out much. but near the edge, where you're looking through the sun's atmosphere at an angle, they become more visible, like bright streaks or patches. Prominences are loops of glowing plasma arcing above the surface. Plasma is just gas that's so hot its atoms have lost some of their electrons, giving it special properties and allowing it to respond to magnetic fields. Prominences follow magnetic field lines like slow ribbons. They can stretch for tens of thousands of miles, great arcs of glowing gas suspended above the sun's surface, held in place by invisible magnetic forces. Some prominences are stable, lasting for days or even weeks. Others are more dynamic, rising and falling, sometimes erupting outward into space. Many solar features are beautiful examples of physics staying organised. Despite the heat, despite the chaos of all that gas churning and boiling, the sun's magnetic field creates structure. It organises the chaos into patterns, loops, arcs, spots, bright regions and dark regions. It's a reminder that even in extreme environments, physics still works, still creates order, still follows rules. Just one more small fact, and then we drift. The corona is the sun's outer atmosphere. It's the part of the sun that extends farthest into space, a vast halo of hot, thin gas that surrounds the visible disk. The corona extends far into space. There's no sharp boundary where the corona ends. It just fades gradually, becoming thinner and thinner until it blends into the solar wind and the space between planets. During a total solar eclipse, when the moon blocks the bright photosphere, the corona becomes visible as a pearly white glow surrounding the darkened sun, with delicate streamers and plumes extending outward. The corona is surprisingly hot compared with the surface below. The photosphere, the visible surface, is about 5,500 degrees Celsius. The corona, despite being farther from the core, is more than 1,000,000 degrees Celsius. This is one of the great mysteries of solar physics. Heat normally flows from hotter regions to cooler regions, so you'd expect the temperature to drop as you move away from the sun's core. But the corona defies that expectation. Scientists study the corona to understand heating and magnetic effects. Current theories suggest that the sun's magnetic field plays a key role, perhaps releasing energy as field lines twist and snap and reconnect, heating the surrounding gas. It's still an active area of research, still something scientists are working to fully understand. The sun releases a steady flow of particles called the solar wind. The corona is so hot that it's not gravitationally bound to the sun. The gas has enough energy to escape, streaming outward in all directions. The solar wind moves outward through the solar system. It's not a fast wind by the standards of, say, a hurricane, but it's steady, flowing past Earth at a few hundred kilometers per second, carrying charged particles, electrons, protons, and heavier ions, out into space. Earth's magnetic field helps deflect many solar wind particles. The Earth has its own magnetic field, generated by the motion of molten iron in its core, and that magnetic field acts like a shield, deflecting most of the solar wind around the planet. The solar wind helps shape Earth's space environment. It compresses the magnetic field on the side facing the sun and stretches it out into a long tail on the night side, creating a region called the magnetosphere. Changes in the solar wind can influence auroras on Earth. When the solar wind is stronger or more turbulent, it can disturb Earth's magnetic field, sending particles spiraling down into the atmosphere near the poles, where they collide with air molecules and create the shimmering lights of the aurora borealis and aurora australis. Most of the time, the solar wind is a quiet, continuous stream. It's not dramatic. It's not something you'd notice unless you had the right instruments. It's just there, a gentle breeze of particles flowing outward from the sun, day after day, year after year, filling the space between worlds. Just one more small fact, and then we drift. The sun has an activity cycle that rises and falls over time. This is often called the solar cycle. The number of sunspots, the frequency of flares, the intensity of the solar wind, all of these vary in a regular pattern. The cycle is about 11 years long on average. Sometimes it's a bit shorter, sometimes a bit longer, but 11 years is a good rough estimate. During higher activity, sunspots are more common. There might be dozens or even hundreds of sunspots visible at any given time, clustered in bands north and south of the sun's equator. During lower activity, sunspots are fewer. At solar minimum, the quiet part of the cycle, there might be weeks or even months when the sun's surface is completely spotless, smooth and bright from edge to edge. The solar cycle is connected to changes in the sun's magnetic field. Over the course of a cycle, the sun's magnetic field gradually becomes more tangled and complex, and then it reorganizes itself, resetting to a simpler state before starting the process all over again. Over a cycle, the sun's magnetic poles switch. The north magnetic pole becomes the south magnetic pole and vice versa. It takes about 11 years for this switch to happen, and then another 11 years to switch back. So a complete magnetic cycle is actually about 22 years. The sun cycle is like a slow heartbeat rather than a sudden switch. It's not that the sun turns on and off. It's more like a rhythm, a gentle rise and fall in activity, a breathing in and breathing out. The cycle affects the frequency of solar flares and eruptions. Solar flares are sudden bursts of energy, bright flashes of light and radiation that can occur when magnetic field lines snap and reconnect. They're more common during solar maximum, the active part of the cycle, but they can happen at any time. Even then, the sun remains a steady, reliable source of light for Earth. The changes in the cycle are real, but they're small compared to the sun's overall output. The amount of light reaching Earth varies by less than 1% over the cycle. You wouldn't notice it in your daily life. The sun still rises and sets, still warms the Earth, still drives the weather and the seasons, regardless of where it is in its cycle. Just one more small fact, and then we drift. The sun is the main source of energy for Earth's climate system. Almost all the energy that drives weather, ocean currents, and the water cycle comes from the sun. Sunlight warms land and oceans. When sunlight strikes the surface of the Earth, some of it is reflected back into space, but most of it is absorbed, heating the ground and the water. Warmth drives evaporation, which helps form clouds and rain. Water evaporates from the oceans, from lakes and rivers, from the soil and from the leaves of plants, rising into the atmosphere as invisible vapor. When that vapor cools and condenses, it forms clouds, and eventually the water falls back to the surface as rain or snow, completing the cycle. Earth's seasons are caused by Earth's tilt, not Earth's distance from the sun. Earth's orbit around the sun is nearly circular, so the distance between Earth and the sun doesn't change much over the course of a year. What does change is the angle at which sunlight strikes different parts of the planet. Earth's axis is tilted about 23.5 degrees relative to its orbit, and that tilt means that during part of the year, the northern hemisphere is tilted toward the sun, receiving more direct sunlight and experiencing summer, while the southern hemisphere is tilted away, receiving less direct sunlight and experiencing winter. 6 months later, the situation is reversed. Day length changes through the year because of that tilt. In summer, the sun rises earlier and sets later, giving you more hours of daylight. In winter, the sun rises later and sets earlier, and the days are shorter. At the equator, where the tilt has less effect, day length stays roughly the same all year round. At the poles, the effect is extreme. During summer, the sun never sets, and during winter, it never rises. Sunlight helps set many biological rhythms in living things. Plants and animals, including humans, have evolved in a world where light comes and goes in a regular cycle, and their internal biology reflects that. Morning light is a strong cue for the body's internal clock. When light enters your eyes in the morning, it signals to your brain that it's time to wake up, time to be active. This helps synchronize your circadian rhythm, your internal sense of time, with the external cycle of day and night. The sun's position helps guide animal migration and navigation. Many birds, for example, use the position of the sun in the sky to help them find their way during migration. They have an internal sense of time that allows them to compensate for the sun's movement across the sky, effectively using the sun as a compass. Plants respond to sunlight for growth and timing. They grow toward the light, a process called phototropism, and many plants also track the time of year based on the length of the day, using that information to decide when to flower or when to drop their leaves. Even indoors, your day-night rhythm is still connected to the sun. Even if you spend most of your time inside, away from direct sunlight, the cycle of light and dark still affects you. Artificial light can mimic some of the effects of sunlight, but it's not quite the same. Natural light has a quality, a spectrum, and an intensity that your body recognizes and responds to. The sun, in a sense, is still part of your daily life, even when you're not thinking about it, even when you're asleep. Just one more small fact, and then we drift. The sun is one star among hundreds of billions in the Milky Way. Our galaxy, the Milky Way, is a vast spiral of stars, gas and dust, stretching across about 100,000 light-years. The Sun is just one of those stars located out in one of the spiral arms about halfway, between the centre of the galaxy and the edge. It is a medium-sized star, not the largest type. There are stars much larger than the Sun, giants and supergiants that dwarf it in size and brightness. And there are stars much smaller, red dwarfs that glow faintly and burn their fuel so slowly they could last for trillions of years. The Sun is somewhere in the middle, a perfectly average, ordinary star. The Sun's age is about 4.6 billion years. That's a number so large it's hard to grasp, but it means the Sun is old. Older than any rock on Earth. Older than the Earth itself. The Sun formed from a cloud of gas and dust. Somewhere in the Milky Way, about 4.5 billion years ago, there was a cloud of gas, mostly hydrogen and helium left over from the Big Bang, mixed with heavier elements created in earlier generations of stars. Something, perhaps the shock wave from a nearby supernova, perhaps just the cloud's own gravity, caused the cloud to start collapsing. As it collapsed, it began to spin, and most of the material fell toward the centre, forming the Sun. That same cloud also formed the planets. The leftover material, the part that didn't fall into the Sun, formed a disk around the young star. In that disk, dust grains stuck together, forming larger and larger clumps, and eventually those clumps became the planets, moons, asteroids, and comets of the solar system. Everything you see in the night sky, everything in our solar system, came from that same cloud. The Sun will not shine the same way forever, but its changes are slow. The Sun is slowly getting brighter as it ages, as the helium accumulates in its core and the fusion process becomes slightly more efficient. Billions of years from now, the Sun will run out of hydrogen in its core and begin to change more dramatically, swelling into a red giant and eventually shedding its outer layers. But those changes are so far in the future that they're almost irrelevant. The Sun's life is measured in billions of years. On human timescales, it is wonderfully steady. It has been shining for as long as there has been life on Earth, and it will continue to shine, essentially unchanged, for as long as anyone alive today could ever need to care about. The elements in your body were formed in earlier generations of stars. The hydrogen in your body is primordial, left over from the Big Bang, but the carbon, nitrogen, oxygen, and all the other heavier elements were created inside stars that lived and died long before the Sun was born. Those stars fused lighter elements into heavier ones, and when they died, some quietly, some in spectacular supernova explosions, they scattered those elements into space, enriching the gas clouds that would eventually form new stars and planets. The Sun is part of that long chain of cosmic recycling. The atoms in your body, the iron in your blood, the calcium in your bones, all of it came from stars. You are quite literally made of stardust, and the Sun is the latest star in a long lineage to illuminate your world. Just one more small fact, and then we drift. Sunlight in the morning can help set your circadian rhythm for the day. Your body has an internal clock, a biological timer that runs on a cycle of about 24 hours, and light is the main signal that keeps that clock synchronized with the outside world. When light enters your eyes, especially bright blue-rich light like the kind you get from the Sun in the morning, it sends a signal to a part of your brain called the suprachiasmatic nucleus, which acts as the master clock for your body. That signal tells your brain it's daytime, it's time to be awake and alert, and it helps set the timing for all the other rhythms in your body. When you feel hungry, when you feel sleepy, when your body temperature rises and falls. Darkness at night helps your brain prepare for sleep. When the Sun sets and light levels drop, your brain starts to produce melatonin, a hormone that makes you feel drowsy and helps you fall asleep. The absence of light is just as important as the presence of light, a signal that tells your body it's time to rest. The Sun's daily cycle is a gentle cue your body has evolved with. For millions of years, for all of human history until very recently, people lived their lives in sync with the Sun. They woke when the Sun rose and slept when it set. Artificial light has changed that, allowing us to stay awake long after dark, but our biology still remembers the old pattern. The Sun's rhythm is still written into our cells. Warmth from sunlight can be stored in walls, floors, and oceans. During the day, sunlight heats surfaces, and those surfaces hold on to that heat for a while, releasing it slowly over time. A brick wall or a concrete floor can absorb heat during the day and radiate it back out at night, keeping a room warm even after the sun has set. The oceans, with their vast capacity to store heat, absorb sunlight during the summer and release it during the winter, moderating the climate and keeping temperatures from swinging too wildly. Evening comfort often comes from the day's heat slowly releasing. When you sit outside on a warm evening, the warmth you feel might not be from the sun directly. It might have set already, but from the heat that the ground and the buildings absorb during the day, now gently radiating back out into the cooling air. The sun's light can feel like a quiet memory, present even after it's gone. Even when the sun is below the horizon, its light lingers. The sky stays bright for a while after sunset, illuminated by sunlight scattering off the atmosphere. And even when the sky is fully dark, the warmth remains, the heat stored in the earth and the air, a reminder that the sun was there, that it will be there again. You don't need to think about the sun for it to keep working. It doesn't need your attention or your awareness. It just keeps shining, keeps warming the earth, keeps driving the cycles of weather and life, completely indifferent to whether anyone notices. The sun holds the solar system steady with gravity. Its immense mass creates a gravitational well that keeps everything in orbit, from Mercury, closest to the sun, to Neptune and the distant reaches of the Kuiper Belt. The planets don't fall into the sun because they're moving, orbiting, their sideways motion balanced against the sun's pull. And they don't fly off into space because the sun's gravity keeps them tethered. It's a stable arrangement, one that has lasted for billions of years and will last for billions more. Tonight, you can let that steadiness become a feeling of safety. The sun is out there, even though you can't see it right now, even though it's nighttime where you are. It's still shining, still holding everything together, still doing what it has always done. There's something comforting in that, in knowing that some things are constant, that some things can be relied upon. The sun will rise again, in its own time, and you can rest until then. You don't need to worry about it. You don't need to do anything. The sun will take care of itself, and the world will turn and morning will come, as it always has, as it always will. Just one more small fact and then we drift. But there are no more facts. There's just this moment, this quiet, this slow release of the day. You've followed the sun from its core to its corona, from its birth billions of years ago to the light that touched your face this morning. You've learned about layers and cycles, about fusion and magnetic fields, about the gentle ways the sun shapes your world and your life. And now, all of that can fade away. You don't need to remember any of it. You don't need to hold on to the facts or the numbers or the names. They were just here to give your mind something to follow, something calm and steady to trace as you let go of the day's thoughts and worries. The sun is still out there, doing its work, burning hydrogen into helium, sending light streaming out into space. It doesn't need you to understand it. It doesn't need you to think about it. It just keeps going, patient and constant, a quiet anchor in the vastness of space. And you can take that constancy with you into sleep, a sense that the universe is orderly, that the cycles continue, that there's no rush, no urgency, nothing that needs your attention right now. Your breathing has slowed, the tension in your shoulders is eased, the thoughts that were racing through your mind have quieted. There's just the rhythm of your breath, the weight of your body sinking into the bed, the gentle darkness behind your closed eyes. The sun's story is over for tonight, but the sun itself continues, shining somewhere beyond the horizon, warming the other side of the world, lighting someone else's morning while you rest. Let your mind wander if it wants to wander. Let it drift to the image of the sun as a glowing sphere, layers upon layers of hot gas, slowly churning, slowly rotating, the core burning bright at the center, the surface shimmering with granules and spots, the corona reaching out into space like a halo. Or let it drift to something simpler, just the feeling of sunlight, warm on your skin, the way it looks filtering through leaves or reflecting off water. Or let it drift to nothing at all, just the soft darkness, the quiet, the stillness. There's no need to fight sleep. There's no need to force anything. Sleep will come in its own time, just as the sun will rise in its own time. You can trust that. You can let go. The sun holds the planets in their orbits with gravity steady and reliable, And in the same way, sleep will hold you, gently, inevitably. You're safe here. You're allowed to rest. The day is done. The facts are done. The sun is shining somewhere, and you are here, breathing slowly, letting go, drifting. The sun's light travels 8 minutes to reach Earth, but you don't need to wait for anything. You're already where you need to be. The warmth is already here, stored in the walls, in the air, in the memory of the day. The light is already here, even in the darkness, a soft presence, a quiet knowing that morning will come. And until then, there is only this: the slow, steady rhythm of your breath, the feeling of your body at rest, the gentle pull of sleep drawing you deeper, deeper into warmth, into darkness, into the quiet place where thoughts dissolve and nothing is required of you. Just one more small fact, and then we drift. But we've already drifted. We're drifting now. The sun is a star at the center of our solar system, and you are here, at the center of your own quiet moment, letting everything else fall away. The facts about the sun, the science, the numbers, they're all fading now, becoming less distinct, less important, until they're just a soft murmur, a distant hum, something that might have been interesting once, but now is just part of the background, part of the gentle static that lulls you towards sleep. The sun will be there tomorrow. It will rise as it always does, pouring light over the horizon, warming the air, starting the cycle again. But that's tomorrow's concern, not tonight's. Tonight, you rest. Tonight, you let the sun do its work without you. Let the earth turn without your attention. Let the universe continue its slow, steady rhythms while you sink into sleep. The sun holds the solar system steady, and sleep holds you steady, and everything is exactly as it should be. The granules on the sun's surface rise and fall, each one lasting only minutes before it breaks apart and reforms, a constant churning, a constant renewal. Your thoughts are like that, rising and falling, appearing and dissolving, and you don't need to hold on to any of them. Let them rise, let them fall, let them drift away like the solar wind, streaming out into space, carrying particles of worry and tension and the remnants of the day far, far away from you until there's nothing left but stillness. The corona is surprisingly hot, hotter than the surface below it, and no one fully understands why. It's a mystery, one of many mysteries in the universe, and that's okay. You don't need to solve it. You don't need to understand everything. Some things can remain unknown, unexplained, soft around the edges, and that doesn't diminish them. The sun is beautiful and complex and ancient, and you are here, breathing, resting, alive in this moment, and that's enough. 8 minutes. That's how long it takes sunlight to reach Earth. 8 minutes of travel through the void, crossing 93 million miles of empty space, and then it arrives, gentle and warm, touching the surface of the planet, touching your skin, becoming part of your day. But those 8 minutes are nothing compared to the time it took for that light to journey from the core to the surface. Hundreds of thousands of years of bouncing and scattering, a slow, patient escape from the heart of the sun. Everything takes time. Everything unfolds at its own pace. Even light, the fastest thing in the universe, needs time to travel. And you, too, can take your time. You can let sleep come slowly, naturally, without rushing, without forcing. The sun's magnetic field twists and tangles, creating sunspots and prominences, loops of glowing plasma suspended in space, held by invisible forces. Your thoughts are tangled too, threads of the day woven together, and now you can let them untangle, let them smooth out, let them release their hold on you. There's nothing you need to figure out right now. There's nothing you need to plan or worry about or solve. It can all wait. It can all dissolve into the quiet. The solar cycle rises and falls, 11 years from peak to peak, a slow heartbeat, a breathing in and out of activity. Your own breath rises and falls, in and out, a rhythm you don't have to think about, a rhythm that continues on its own, steady and reliable. You can follow that rhythm if you like, or you can let it fade into the background, just another part of the quiet, another part of the stillness. The sun is one star among hundreds of billions, ordinary and average, Nothing special except that it's ours, except that it's close enough to warm us, close enough to light our days, and you are one person among billions, ordinary and average in some ways, unique in others, and tonight that doesn't matter. Tonight, you're just here, resting, part of the vast, quiet universe, connected to the sun by 8 minutes of light, connected to the earth by gravity, connected to sleep by the simple, inevitable need to rest. The atoms in your body came from stars, formed in the cores of ancient suns, scattered into space when those stars died, gathered together again in the cloud that became our solar system. You are stardust, shaped by billions of years of cosmic history, and tonight you return to the stars in a way, returning to the quiet, the darkness, the stillness from which everything came. Sleep is a kind of return, a letting go, a sinking back into the void that holds everything. The sun doesn't need you to watch it. It doesn't need your awareness or your attention. It shines whether you're awake or asleep, whether you're thinking about it or not. And in the same way, your body doesn't need your attention to keep breathing, to keep your heart beating, to keep you alive. You can let go of control. You can trust your body to do what it needs to do. You can trust sleep to come, to hold you, to carry you through the night. Just one more small fact, and then we drift. But we've already drifted so far. We're already deep in the quiet, deep in the soft darkness, and there are no more facts, no more explanations, no more words. There's just this, the gentle weight of your body, the slow rhythm of your breath, the feeling of letting go, of sinking, of drifting down into sleep like sunlight sinking through water, soft and golden and fading into the deep. The sun will rise again in its own time and you can rest until then. The next story is about to begin. Please relax and enjoy. The moon hangs in our sky at an average distance of about 238,855 miles from Earth, though this number shifts constantly as our natural satellite follows its elliptical path around our planet. This distance, while vast by human standards, represents one of the closest celestial relationships in our solar system. The moon orbits Earth roughly once every 27.3 days, measured relative to the background stars, though the cycle from new moon to new moon takes slightly longer at 29.5 days due to Earth's own motion around the sun. This gentle, perpetual dance has continued for billions of years, creating the rhythmic patterns that govern tides, influence ecosystems, and provide a steady companion in our night sky. The moon's formation remains one of the most fascinating stories in planetary science, and the leading explanation involves a collision of almost unimaginable violence that paradoxically created the serene object we see today. Scientists currently think that about 4.5 billion years ago, when Earth was still very young and hot, a Mars-sized object collided with our planet in a grazing impact. This impactor, sometimes called Theia by researchers, struck Earth at just the right angle and speed to blast enormous amounts of material into orbit rather than merging completely or bouncing away. The debris from this catastrophic encounter, a mixture of material from both Earth's outer layers and the impactor itself, formed a ring of molten rock and vapour circling our planet. Over time, measured in years and centuries and millennia, this ring gradually coalesced through gravitational attraction, building up into the moon we know today. Evidence for this giant impact hypothesis comes from multiple sources, including the similar composition of Earth and moon rocks, the moon's relatively small iron core compared to Earth's, and the angular momentum of the Earth-Moon system. When we look at the moon's surface, we see a landscape frozen in time, preserving a record of the solar system's violent youth. The most prominent features visible even to the naked eye are the dark patches called Maria, a Latin word meaning seas, though no water flows there and perhaps never has. These Maria formed between 3.8 and 3 billion years ago during a period of intense asteroid and comet bombardment. When these massive objects struck the moon's surface, they created enormous impact basins that subsequently filled with molten basaltic lava flowing up from the moon's interior. The lava spread across the basin floors in vast sheets, sometimes hundreds of feet thick, before cooling and solidifying into the smooth, dark plains we observe today. The lighter areas surrounding these dark Maria are the lunar highlands, representing the moon's original crust, which formed when the early moon's surface was a global ocean of molten rock. As this magma ocean slowly cooled over millions of years, lighter minerals floated to the top while denser materials sank, creating the layered structure that produced the bright highland rocks. The surface of the moon bears the scars of billions of years of impacts, and examining these craters tells us much about the history of our corner of the solar system. Unlike Earth, where erosion from wind and water, tectonic activity, and biological processes constantly reshape the surface, the moon preserves its impact record with remarkable fidelity. The largest impact basin on the moon's near side is the Imbrium Basin, measuring about 750 miles across, created by an impact so powerful it sent shockwaves through the entire moon and scattered debris across the lunar surface. The youngest large crater visible through binoculars is Tycho, a relatively fresh impact feature only about 108 million years old, whose bright rays of ejected material extend across much of the moon's southern hemisphere. These rays appear bright because the impact excavated fresh material from beneath the lunar surface, material that hasn't yet been darkened by billions of years of exposure to solar radiation and micrometeorite bombardment. The process that darkens lunar soil happens slowly but inexorably, as energetic particles from the sun and tiny impacts gradually alter the chemical structure of the surface minerals. The moon's lack of atmosphere has profound implications for its surface conditions and appearance. Without air to scatter sunlight, the lunar sky remains utterly black even during the day, with stars visible alongside the sun for any observer standing on the moon. The absence of atmospheric protection means that the lunar surface experiences temperature extremes unknown on Earth, ranging from about 260 degrees Fahrenheit in direct sunlight at the lunar equator to minus 280 degrees Fahrenheit in the permanent shadows near the poles. These temperatures shift not gradually but abruptly, with the boundary between sunlight and shadow marking a transition of hundreds of degrees within the span of a few feet. The moon's day-night cycle lasts nearly a month by Earth standards, with each location experiencing about 14 Earth days of continuous sunlight followed by 14 Earth days of darkness. This extended exposure to solar radiation during the lunar day heats the surface slowly but thoroughly, while the equally long night allows heat to radiate into space without atmospheric insulation to retain warmth. One of the moon's most remarkable characteristics, often taken for granted but actually quite unusual, is that we always see the same face from Earth. This phenomenon results from a process called synchronous rotation or tidal locking, where the moon's rotation period exactly matches its orbital period around Earth. This wasn't always the case. When the moon first formed, it likely rotated much faster. However, Earth's gravity creates tidal bulges in the moon's structure, not just in any hypothetical oceans, but in the solid rock itself. As the moon rotated, these bulges tried to move, but Earth's gravity pulled on them, creating friction and gradually slowing the moon's rotation. Over hundreds of millions of years, this tidal friction continued until the moon's rotation rate synchronized with its orbit, leaving the same hemisphere perpetually facing Earth. The far side of the moon, never visible from Earth without spacecraft, differs noticeably from the near side, possessing far fewer maria and a thicker crust. Scientists think this asymmetry may relate to Earth's influence during the moon's formation and early history, though the complete explanation remains an active area of research. The moon exerts a powerful influence on Earth through gravitational tides, creating a twice-daily rhythm in our oceans that has shaped coastal ecosystems and human maritime activities throughout history. The basic mechanism of tides involves the gravitational attraction between the moon and Earth's water, though the actual physics proves more subtle than simple attraction. The moon's gravity pulls on the side of Earth nearest to it, with slightly more force than it pulls on Earth's centre, which in turn experiences more pull than the far side. This differential gravitational force stretches Earth very slightly into an oval shape, with bulges on both the near and far sides. Because Earth's surface is mostly solid rock, this stretching amounts to only inches, but the oceans, being fluid, respond more dramatically, creating the oceanic tides. As Earth rotates beneath these tidal bulges, different locations pass through high and low tide, approximately every 12 hours and 25 minutes. The Sun also creates tides, though its effect is smaller than the Moon's despite the Sun's vastly greater mass, because tidal force depends on the difference in gravitational pull across Earth's diameter, and the Moon's proximity makes its differential effect stronger. The twice-monthly cycle of spring and neap tides demonstrates the interplay between solar and lunar tidal influences. Spring tides, which occur during new and full moons, happen when the Sun and Moon align and their tidal effects combine, creating higher high tides and lower low tides than average. The term spring refers not to the season but to the idea of the tide springing or rising higher. Neap tides occur during the moon's first and third quarters when the sun and moon form a right angle as seen from Earth, causing their tidal effects to partially cancel each other, resulting in more moderate tidal ranges. The magnitude of tides varies considerably depending on local geography, with some locations experiencing tidal ranges of only a foot or two, while others, particularly in narrow bays and estuaries where tidal waters are funneled and amplified, see ranges exceeding 50 feet. The Bay of Fundy in Canada holds the record for the highest tides on Earth, with a maximum range of about 53 feet, creating dramatic transformations of the coastline twice daily. Beyond their effects on ocean levels, tides have more subtle but profound impacts on Earth's rotation and the moon's orbit. The friction between tidal waters and the ocean floor, along with the deformation of Earth's solid body, dissipates energy and gradually slows Earth's rotation. This lengthening of Earth's day proceeds at a rate of about 1.7 milliseconds per century, a tiny change imperceptible in human lifetimes but significant over geological time. When Earth rotates with shallow seas sloshing across continental shelves, the tidal friction becomes particularly effective at extracting rotational energy. This energy doesn't vanish but rather transfers to the moon's orbital motion through a complex gravitational interaction involving the slight offset of Earth's tidal bulge. Because Earth rotates faster than the moon orbits, Earth's rotation drags the tidal bulge slightly ahead of the direct Earth-Moon line. This offset bulge then gravitationally pulls on the moon in the direction of its orbital motion, accelerating the moon and causing it to slowly spiral outward. Laser ranging measurements, which bounced light off reflectors placed on the lunar surface by Apollo astronauts, confirm that the moon recedes from Earth at about 1.5 inches per year. Looking backward in time, this lunar recession means the moon was closer to Earth in the past and much closer in the very distant past. When the moon first formed at perhaps 10 to 15,000 miles from Earth, compared to today's roughly 240,000 miles, it would have appeared enormous in Earth's sky, subtending an angle perhaps 15 to 20 times larger than today. The tides raised by this nearby moon would have been correspondingly stronger, possibly reaching heights of hundreds of feet and occurring every few hours as the young Earth spun, rapidly on its axis. Some scientists have speculated that these extreme tides may have influenced the development of Earth's early crust, and perhaps even played a role in mixing the primordial oceans in ways that affected the chemistry relevant to the origin of life, though such ideas remain highly speculative. The moon's gradual distancing has another eventual consequence that becomes apparent during solar eclipses. Currently, the moon's apparent size in our sky matches the sun's apparent size almost exactly, a cosmic coincidence that allows for the spectacular phenomenon of total solar eclipses, where the moon can precisely cover the sun's bright disk while leaving the faint outer atmosphere, the corona, visible. This match occurs because although the sun is about 400 times larger than the moon, it's also about 400 times farther away, making the two objects appear nearly the same size from Earth. However, as the moon continues to recede, its apparent size will gradually shrink. In roughly 600 million years, the moon will be too far from Earth to completely cover the sun, and total solar eclipses will become impossible, replaced by only annular eclipses where a ring of sunlight remains visible around the moon's silhouette. Solar eclipses themselves follow predictable patterns thanks to the regular geometry of the Earth-Moon-Sun system, though predicting exactly where on Earth an eclipse will be visible requires careful calculation. A solar eclipse can occur only during a new moon, when the moon passes between Earth and the sun, but not every new moon produces an eclipse because the moon's orbit around Earth is tilted about 5 degrees relative to Earth's orbit around the sun. This tilt means the moon usually passes above or below the sun from Earth's perspective. Eclipses happen only when a new or full moon coincides with the moon crossing the plane of Earth's orbit, points called nodes. The geometry of these orbital intersections repeats in a cycle called the Saros, lasting approximately 6,585 and 1/3 days, or about 18 years, 11 days, and 8 hours. After one Saros cycle, the Sun, Earth and Moon return to nearly the same geometric arrangement, producing a similar eclipse. However, the extra 1/3 day in the cycle means the eclipse occurs about 8 hours later in Earth's rotation, shifting the visibility path about 120 degrees westward. The narrow path of totality during a solar eclipse, typically only about 70 to 100 miles wide, results from the moon's shadow having two parts. The inner darker shadow called the umbra creates the path of totality where the sun is completely blocked, while the outer, lighter shadow called the penumbra creates a region where the sun is only partially blocked. Because the moon is relatively small, and its distance from Earth varies as it orbits, the umbra sometimes fails to reach Earth's surface at all, creating annular eclipses where the moon appears slightly smaller than the sun. The maximum duration of totality during a solar eclipse is about 7.5 minutes, achieved when the moon is at its closest point to Earth and moving most slowly across the sun's face, though most total solar eclipses are considerably shorter, typically lasting between 2 and 3 minutes. Lunar eclipses present a different spectacle, occurring when Earth passes between the sun and moon, causing Earth's shadow to fall on the lunar surface. These eclipses can happen only during a full moon and are visible from the entire nighttime half of Earth, unlike solar eclipses which are visible only from specific narrow paths. During a total lunar eclipse, the moon doesn't disappear completely, but instead often takes on a coppery red colour. This colouring results from sunlight passing through Earth's atmosphere and bending into the shadow region. Earth's atmosphere scatters blue light more effectively than red light, the same phenomenon that makes sunsets red and the sky blue. So the light reaching the moon during an eclipse has had its blue components removed, leaving primarily red wavelengths to illuminate the lunar surface. The exact colour and brightness of the eclipsed moon depends on Earth's atmospheric conditions at the time, with volcanic eruptions or unusual dust content creating darker or more colourful eclipses. The moon's interior structure has been revealed through various means, including seismometers placed by Apollo astronauts and analysis of the moon's gravitational field and physical properties. The moon possesses a layered structure somewhat similar to Earth's, with a crust, mantle, and core, though the proportions differ significantly. The lunar crust ranges from about 25 miles thick on the near side to about 40 miles thick on the far side, this asymmetry representing one of the moon's puzzling features. Below the crust lies the mantle, composed primarily of silicate rocks rich in magnesium and iron, extending down to a depth of roughly 900 miles. The deepest moonquakes detected by Apollo seismometers originated at depths of about 600 to 800 miles, likely caused by gravitational tides from Earth stressing the lunar interior. These deep moonquakes occurred repeatedly at the same locations and times during the moon's orbit, indicating they relate to specific tidal stress patterns. The lunar core, much smaller relative to the moon's size than Earth's core is to Earth's size, consists of a solid inner core and possibly a liquid outer core, together measuring perhaps 300 miles in radius. This small core helps explain why the moon lacks a global magnetic field today, though measurements of lunar rocks reveal that some possessed magnetization, requiring an ancient lunar magnetic field. Scientists think the moon may have generated a magnetic field through a dynamo process early in its history when the core was entirely molten and convecting. But as the moon cooled and much of the core solidified, this dynamo ceased. Some localized magnetic anomalies on the lunar surface, regions where rocks show unexpectedly strong magnetization, might represent impacts that occurred while the lunar dynamo was still operating, with the shock of the impact effectively freezing the ambient magnetic field into the rocks as they cooled. The Apollo program of the 1960s and 70s represents humanity's most direct interaction with the moon, placing 12 astronauts on the lunar surface across 6 missions between 1969 and 1972. These missions returned 842 pounds of lunar rocks and soil, samples that remain the primary source of detailed information about lunar composition and history. The rocks revealed that the moon's maria consist of basalt similar to volcanic rocks on Earth, but with subtle compositional differences, including lower water content and different relative abundances of certain elements. The highland rocks proved to be largely an orthosite, a light-coloured rock rich in the mineral plagioclase feldspar, consistent with the hypothesis that they formed as light minerals floated to the top of a cooling magma ocean. Dating these rocks using radioactive decay systems showed that the highland rocks are extremely ancient, with formation ages of 4.4 to 4.5 billion years, nearly as old as the solar system itself, while the maria basalts are younger, ranging from about 3.8 to 3 billion years old. One surprising discovery from the Apollo samples was the near-complete absence of water in lunar rocks, or more precisely, the near-complete absence of water that was incorporated into minerals as they formed. The lunar rocks are drier than any naturally occurring rocks found on Earth, sometimes described as being drier than the driest terrestrial deserts. This extreme dryness supported the giant impact hypothesis for lunar formation, because the impact would have vaporized water and other volatile substances, allowing them to escape. However, more recent discoveries have complicated this picture slightly. Orbital spacecraft have detected signatures of water ice in permanently shadowed craters near the lunar poles, where temperatures remain cold enough that ice can persist for billions of years. Additionally, very sensitive measurements of Apollo samples have revealed traces of water in volcanic glass beads and in the interiors of some minerals, suggesting the Moon's interior might not be quite as dry as once thought, though it remains extremely dry by Earth standards. The permanently shadowed craters near the Moon's poles represent some of the coldest places in the solar system, with temperatures that may reach as low as -400 degrees Fahrenheit, or perhaps even colder. These cold traps occur because the Moon's axis of rotation is tilted only about 1.5 degrees relative to its orbital plane, compared to Earth's 23.5-degree tilt. This near-vertical orientation means that the floors of deep craters near the poles never receive direct sunlight. Any water molecules that happen to wander into these cold traps, perhaps delivered by comet impacts or produced by interactions between the solar wind and oxygen in lunar rocks, would freeze and remain frozen for geological time periods. Some researchers have speculated that these permanently shadowed regions might contain not just water ice, but also frozen deposits of other volatile substances, including carbon dioxide, ammonia and methane, creating a record of material delivered to the inner solar system over billions of years. The lunar surface experiences constant bombardment by micrometeorites, tiny particles ranging from dust grains to pebbles that strike the Moon at velocities of tens of thousands of miles per hour. Without an atmosphere to burn them up, these particles strike the surface directly, creating microscopic craters and gradually pulverizing the upper layers of rock into a fine powder. This process, operating over billions of years, has created the lunar regolith, a layer of fragmented and broken rock covering the Moon's surface to depths ranging from about 10 feet in the Maria to perhaps 30 feet or more in the highlands. The regolith consists not just of simple crushed rock, but includes glass spherules created when impacts melted rock, particles welded together by impact heat, and fragments excavated from depths and transported far from their origins by large impacts. Walking on the lunar surface, Apollo astronauts found the regolith behaved somewhat like snow, compressing under their boots but also clinging to their spacesuits with surprising tenacity. The constant rain of solar wind particles, primarily protons and electrons streaming from the Sun, affects the lunar surface in subtle but interesting ways. These energetic particles strike the Moon directly without atmospheric shielding and become implanted in the upper layers of regolith grains. Over time, solar wind hydrogen can react with oxygen in lunar minerals to create tiny amounts of water or hydroxyl groups, explaining some of the water signatures detected by spacecraft. The solar wind implantation also creates a very thin and extremely tenuous atmosphere, if it can be called an atmosphere at all, consisting of particles knocked off the surface by impacts and solar wind bombardment. This exosphere is so tenuous that particles almost never collide with each other, following ballistic trajectories more like spacecraft in orbit than like molecules in a gas. The Moon's influence extends beyond physical effects, like tides, to encompass cultural and biological influences that have shaped life on Earth and human civilization. The regular cycles of lunar phases provided early humans with a natural calendar, and many cultures developed lunar or lunisolar calendars to track time and coordinate seasonal activities. The word month derives from moon, reflecting this ancient connection. Some biological organisms synchronize their reproductive cycles with lunar phases, the most famous examples being certain marine species that spawn during specific lunar phases, apparently using moonlight levels or tidal patterns as timing cues. Coral reefs around the world often show synchronized spawning events tied to lunar cycles, releasing eggs and sperm on specific nights following full moons, a strategy that increases the chances of successful fertilization while also potentially overwhelming predators with the sheer abundance of gametes in the water. Whether the Moon affects human biology and behavior beyond providing light at night remains controversial. with many claimed lunar effects failing to hold up under careful statistical analysis. The popular notion that full moons influence human behaviour, causing increased emergency room visits, psychiatric episodes, or births, has been extensively studied and generally not supported by data when proper statistical controls are applied. The term lunacy derives from the Latin word for moon, luna, reflecting ancient beliefs about lunar influences on the mind. But modern evidence suggests these effects were likely either coincidental or caused by confirmation bias. However, the moon certainly influences human activity indirectly by providing illumination during night hours and in pre-industrial societies without artificial lighting. Full moons would have enabled activities impossible during dark nights, potentially affecting sleep patterns and activity rhythms. Future exploration of the moon has become a focus of renewed interest from space agencies and private companies around the world. The motivations include scientific discovery, testing technologies for eventual Mars missions, and potentially utilizing lunar resources. The presence of water. Ice in polar cold traps has attracted particular attention because water can be split into hydrogen and oxygen, providing both rocket propellant and breathable air for future astronauts. The moon's low gravity, about 1/6 that of Earth, means that launching spacecraft from the lunar surface requires far less energy than launching from Earth, potentially making the moon a useful staging point for missions deeper into the solar system. Additionally, the moon's far side offers a unique environment for radio astronomy, shielded from Earth's radio noise by the bulk of the moon itself, allowing potentially unprecedented observations of faint cosmic radio signals. Several space agencies have announced plans for lunar missions in the coming decades, including NASA's Artemis program, which aims to return humans to the moon and establish a sustainable presence there. The technical challenges of maintaining a human presence on the moon include protection from radiation, since the moon lacks both a magnetic field and atmosphere to shield against solar and cosmic radiation, and dealing with the abrasive lunar dust, which caused significant problems for Apollo equipment, despite missions lasting only a few days. The temperature extremes and the long lunar day-night cycle pose additional engineering challenges for any permanent facilities, which would need to either store energy for the 14-day night or be located at special locations near the poles where elevated terrain can receive nearly continuous sunlight. The moon's geology continues to present puzzles and opportunities for research. The Maria, while broadly understood as ancient lava flows, show detailed features that reveal information about lunar volcanic processes. Some Maria contain sinuous channels called rills, winding features that sometimes extend for hundreds of miles and may represent either collapsed lava tubes or channels carved by flowing lava. The lunar surface also contains mysterious dome structures, thought to be volcanic in origin, and straight or curved features called wrinkle ridges that may represent buckling of the lava flows as they cooled and contracted, or as the weight of the lava compressed the underlying crust. Understanding these features helps planetary scientists piece together the moon's volcanic history and compare it to volcanic processes on Earth and other solar system bodies. The lunar highlands, making up about 83% of the moon's surface, preserve a record of the intense bombardment that all inner solar system bodies experienced early in their histories. This period of heavy bombardment, lasting from the solar system's formation until about 3.8 billion years ago, shaped the surfaces of the Moon, Mercury, Mars, and even Earth, though Earth's active geology has erased most direct evidence from our planet's surface. The timing and intensity of this bombardment remains somewhat uncertain, with some evidence suggesting a spike in impact rates around 3.9 billion years ago, sometimes called the Late Heavy Bombardment. Whether this represents a true increase in impact rates or simply a bias in the preservation of evidence remains debated, but studying lunar craters and their ages helps scientists understand this important phase of solar system evolution. The Moon has no plate tectonics like Earth, where large sections of crust move relative to each other, creating mountains, ocean basins, and recycling surface material into the interior. The Moon's smaller size meant it cooled more rapidly than Earth, and its interior appears to be largely solid today, lacking the vigorous convective motions in the mantle that drive Earth's plate tectonics. Without this geological recycling and without erosion from water or atmosphere, the lunar surface preserves features billions of years old with remarkable clarity. This geological stillness makes the Moon valuable as a record of solar system history, but It also means that the Moon's active geological history was relatively brief. Most of the Moon's volcanic activity occurred between about 3.8 and 3 billion years ago, with little evidence for volcanic activity in the most recent billion years, though some researchers have argued for occasional small eruptions in more recent times based on fresh-looking deposits. The Moon's gravitational field shows interesting variations that reveal information about its internal structure. Concentrations of mass beneath some of the large impact basins, called mascons for mass concentrations, create regions of slightly stronger gravity that can affect the orbits of spacecraft. These mascons probably represent the dense mantle material that welled up after the giant impacts, partially filling the basins before the lava flows arrived. The presence of mascons indicates that the lunar lithosphere, the strong outer shell of the Moon, was thick enough to support these mass concentrations, without the basins collapsing back to equilibrium, suggesting the Moon had already cooled and developed a substantial lithosphere by the time the large impacts occurred. One of the curious aspects of the Moon's orbit is its slight eccentricity, meaning the orbit is not perfectly circular but slightly elliptical. This eccentricity causes the Moon's distance from Earth to vary from about 225,000 miles at perigee, the closest point, to about 252,000 miles at apogee, the farthest point. When a full moon occurs near perigee, sometimes called a supermoon in popular media, the Moon appears about 14% larger and about 30% brighter than when full moon occurs near apogee. However, this size difference proves difficult to detect by eye without careful measurement or comparison photographs. The Moon's orbital eccentricity also varies over long time periods due to gravitational perturbations from the Sun and planets, though these variations are small and gradual. The Moon's orbit is also inclined about 5 degrees to the ecliptic, the plane of Earth's orbit around the Sun, and this inclination varies slightly over time in a cycle lasting about 18.6 years. This variation in orbital inclination affects how high the Moon appears in the sky from different latitudes on Earth, and influences the patterns of tides. During the major standstill, when the Moon's orbital inclination reaches its maximum, the Moon can appear very high in the sky as seen from locations at high latitudes, while during the minor standstill, the Moon's range of positions becomes more restricted. Ancient monuments such as some stone circles in Britain appear to have been aligned with these lunar standstill positions, suggesting that prehistoric peoples tracked these cycles carefully, though the purposes of such tracking remain somewhat speculative. The Moon's surface contains numerous features named after scientists, philosophers, and other notable figures, following a tradition established in the 17th century by early telescopic observers. The lunar highlands contain craters named after Copernicus, Kepler, Tycho, and many other figures from the history of science and philosophy, while the Maria bear Latin names such as Mare Tranquillitatis, the Sea of Tranquility, where Apollo 11 landed, and Mare Imbrium, the Sea of Rains. Some features bear more whimsical names, like the crater Hadley Rill, named after John Hadley, who invented the reflecting sextant, which became the landing site for Apollo 15. The far side of the Moon, first photographed by Soviet spacecraft in 1959, contains additional name features including the Mare Moscoviense, the Moscow Sea, and craters named after space exploration pioneers. The question of whether the Moon could support life in any form has generally received a negative answer given the absence of atmosphere, liquid water, and protection from radiation. However, the discovery of more water than previously suspected, particularly the ice in permanently shadowed craters, raises interesting if highly speculative possibilities. If protected environments existed, perhaps in lava tubes or beneath the surface where ice deposits might exist, could these harbour simple microorganisms? Most scientists consider this extremely unlikely given what we know about the Moon's history and conditions, but the question illustrates how our understanding of possible habitats for life has expanded. More practically, if humans establish a permanent presence on the Moon, the question of preventing contamination becomes important both to protect any potential lunar science from terrestrial contamination and to avoid introducing Earth organisms into the lunar environment. The Apollo program left behind not just footprints and scientific instruments, but also several types of ongoing experiments that continue to provide data decades later. The most successful of these has been the laser-ranging retroreflectors, arrays of corner cube prisms that reflect laser beams directly back to their source. By timing how long laser pulses take to travel from Earth to the Moon and back, scientists can measure the Earth-Moon distance with remarkable precision, currently accurate to about a millimetre. These measurements have confirmed the gradual lunar recession, tested predictions of general relativity, and provided information about variations in Earth's rotation. The retroreflectors require no power and have no moving parts, allowing them to function indefinitely, though their reflective efficiency has decreased somewhat over the decades, possibly due to coating of lunar dust. The Moon's lack of global magnetic field today contrasts with evidence that some lunar rocks formed in the presence of a strong magnetic field billions of years ago. Understanding how and when the lunar magnetic field operated and eventually shut down provides clues about the Moon's thermal evolution and internal dynamics. The generation of magnetic fields in planetary bodies generally requires a dynamo process where flowing, electrically conducting fluid, usually liquid metal in a planet's core, converts kinetic energy into magnetic energy. For the Moon to have sustained a dynamo, its core must have been molten and convecting, which requires sufficient heat. As the Moon cooled over time, the core would have begun to solidify, potentially shutting down convection and ending the dynamo. Some researchers have proposed alternative mechanisms for the ancient lunar magnetic field, including the possibility that the giant impact that formed the Moon left the early Moon rotating much faster than today, and that this rapid rotation helped sustain a dynamo even with a smaller and cooler core than would normally be required. When astronauts first landed on the Moon, one concern was how the fine lunar dust would behave. The regolith particles, never having been rounded by water or wind erosion, retain sharp edges and angular shapes that make them particularly abrasive. Additionally, static electricity and the lack of moisture can cause the dust particles to cling to surfaces with surprising tenacity. Apollo astronauts reported that the dust worked its way into seals and mechanisms despite precautions, and they could smell the dust when it entered the lunar module, describing it as similar to gunpowder or spent fireworks. This smell probably resulted from chemical reactions when the dust, which had been altered by solar wind bombardment and vacuum conditions, suddenly encountered oxygen and moisture in the cabin atmosphere. Understanding and mitigating the effects of lunar dust represents one of the engineering challenges for future lunar missions, as prolonged exposure to the abrasive, clingy dust could damage equipment and potentially pose health hazards to astronauts. The Moon's surface temperature varies not just between day and night, but also with depth below the surface. While the surface experiences extreme temperature swings, measurements from Apollo experiments showed that at depths of only a few feet, the temperature becomes stable at about -35 degrees Fahrenheit, representing an average of the surface temperature variations. This temperature stability with depth occurs because the regolith acts as an insulating layer, with the upper portion responding to daily temperature changes while deeper material maintains an equilibrium temperature. This property might prove useful for future lunar habitats, which could potentially maintain more stable temperatures by being partially buried in regolith, providing both thermal stability and some radiation shielding. The phenomenon of Earthshine, where Earth's reflected sunlight illuminates the Moon's night side, creates the beautiful sight of the dark portion of the crescent moon glowing faintly, sometimes called the Old Moon in The New Moon's Arms in poetry. This Earthshine is bright enough that if you were standing on the Moon's night side looking at Earth, our planet would provide much more light than the full moon provides on Earth, both because Earth is larger and because Earth's atmosphere and clouds make it more reflective. An observer on the Moon would see Earth go through phases opposite to the lunar phases seen from Earth, with a full Earth visible from the Moon during the new moon phase and a new Earth during the full moon. Additionally, Earth would appear to hang nearly motionless in the lunar sky, slowly rotating on its axis but not rising or setting for an observer on the lunar near side, while Earth would never be visible at all from the lunar far side. The Moon stabilizes Earth's axial tilt through its gravitational influence, preventing the large variations in obliquity that would otherwise occur over millions of years due to gravitational perturbations from other planets. Without the Moon, Earth's obliquity might vary chaotically between 0 and 85 degrees, creating extreme climate variations that would make the planet much less hospitable for life. The Moon's presence keeps Earth's obliquity confined to a relatively narrow range around 23.5 degrees, varying by only about a degree or two over tens of thousands of years. This stability has likely been important for the development of complex life on Earth, providing relatively stable climate zones and preventing the catastrophic climate shifts that large obliquity variations would cause. This represents one of the subtle but profound ways the moon has influenced Earth's evolution and habitability. Looking at the moon through a telescope reveals a wealth of detail impossible to see with the naked eye. The curved line separating the illuminated and dark portions of the moon, called the terminator, offers the best views of surface features because the low angle of sunlight near the terminator creates long shadows that highlight topographic variations. Craters, mountains, and valleys that might appear flat and washed out in high, overhead sun stand out in sharp relief near the terminator. The moon's features show best not during the full moon, despite maximum brightness, but during the quarter phases when the terminator bisects the visible face, and shadows reveal three-dimensional structure. Observers with telescopes can see the central peaks inside some large craters, mountainous terrain in the highlands, the smooth plains of the Maria, and the bright ray systems extending from young craters. The moon has inspired countless works of art, literature, and music throughout human history, serving as a symbol of romance, mystery, and aspiration. From ancient myths explaining the moon's phases and features to science fiction stories imagining lunar inhabitants or bases, the moon occupies a unique place in human culture. The achievement of landing humans on the moon in 1969 represented not just a technical accomplishment, but a moment when humanity first set foot on another celestial body, expanding our physical presence beyond Earth. The famous photograph of Earth rising over the lunar horizon, taken by Apollo 8 astronauts in December 1968, provided a new perspective on our home planet as a small, beautiful, fragile world hanging in the void, an image that helped inspire environmental awareness and a sense of our common humanity. The phases of the moon result from the changing angles between the Sun, Earth, and Moon as the moon orbits Earth. During the new moon, the moon lies between Earth and the Sun, with its illuminated side facing away from Earth, making it invisible except during solar eclipses. As the moon continues its orbit, a thin crescent becomes visible, growing thicker each night as more of the illuminated face becomes visible from Earth. At the first quarter, half of the moon's face appears illuminated, though the term quarter refers to the moon's position in its orbit rather than the visible fraction. The waxing gibbous moon shows more than half illuminated, until the full moon occurs when Earth lies between the Sun and Moon, and we see the entire illuminated face. The cycle then reverses through waning gibbous, third quarter, and waning crescent before returning to new moon. This entire cycle takes 29.5 days, slightly longer than the moon's orbital period of 27.3 days because Earth's motion around the Sun means the moon must travel slightly more than one complete orbit to return to the same phase. The moon's influence on Earth's rotation, gradually slowing it through tidal friction, means that Earth's day has been lengthening throughout geological history. When the moon first formed, Earth's day may have been only 4 to 6 hours long, compared to today's 24 hours. Evidence for Earth's changing rotation rate comes from multiple sources, including growth patterns in ancient corals and other organisms that recorded daily and annual cycles in their structures. By counting daily growth bands within yearly patterns in fossil corals hundreds of millions of years old, paleontologists have determined that Earth's day has indeed grown longer over time, consistent with the predictions from tidal friction theory. This gradual slowing continues today, adding about 1.7 milliseconds to the day length per century, a change that accumulates enough over many centuries that it becomes necessary to occasionally add leap seconds to our atomic time standards to keep them synchronized with Earth's actual rotation. The moon's surface features include not just craters and Maria, but also mysterious swirl-like patterns visible in some locations, appearing as bright, winding streaks on the surface. These lunar swirls, found in areas such as Reina Gamma and near the far-side crater Mare Magenis, don't obviously correspond to topographic features, but instead appear to be albedo markings, where surface material has different reflective properties. The swirls correlate with local magnetic anomalies, regions where crustal rocks possess stronger than average magnetization. One hypothesis suggests that these magnetic fields, though weak by Earth standards, provide slight protection from solar wind bombardment, preventing or slowing the normal darkening of the soil that occurs over time, thus preserving brighter, fresher-looking material. Alternative explanations involving comet impacts or other processes have also been proposed, but the magnetic shielding hypothesis currently appears most consistent with observations. The Moon's interior, though much less active than Earth's, may not be completely dead geologically. Seismometers placed by Apollo astronauts detected thousands of seismic events during their operating period, ranging from impacts of meteorites and spacecraft to deep moonquakes and thermal quakes, caused by the sudden temperature changes at sunrise. The deep moonquakes, occurring at depths of 600 to 800 miles, appear to result from tidal stresses caused by Earth's gravity flexing the moon slightly as it orbits. These moonquakes are much weaker than typical earthquakes, but occur in clusters at specific locations and times in the lunar month, creating a predictable pattern tied to the moon's orbital position. Thermal moonquakes, caused by the expansion and contraction of surface rocks as they heat in sunlight and cool in shadow, mostly occur near sunrise when surface rocks experience the most rapid temperature changes. Recent analysis of Apollo seismic data using modern techniques has revealed additional information about the lunar interior, including evidence for a partially molten layer at the base of the mantle and confirmation of a small metallic core. The details of the core structure remain somewhat uncertain, with estimates of the solid inner core radius ranging from about 150 to 250 miles, and the liquid outer core perhaps extending to a radius of about 200 to 300 miles. These small sizes, compared to Earth's core, which extends to about half of Earth's radius, help explain why the moon lacks a current magnetic field and provide constraints on models of lunar formation and thermal evolution. Volcanic glasses found in lunar samples provide evidence for fire fountaining, where lava erupted explosively from the lunar interior, spraying droplets that cooled and solidified into tiny glass beads. These pyroclastic deposits sometimes appear as dark halos around small craters or as darker patches on the Maria, representing volcanic material spread across the surface by explosive eruptions rather than flowing as lava. The composition of these glasses reveals information about the moon's interior chemistry, and the presence of the glasses indicates that at least some lunar magmas contained enough dissolved gases to drive explosive eruptions, contrary to the expectation that the moon's interior would be completely dry and unable to produce such eruptions. The gases involved were probably not water vapour, but instead carbon monoxide or sulfur compounds. The moon affects life on Earth in subtle ways beyond the obvious tides. The lunar illumination cycle influences the behaviour of many nocturnal animals, with some species more active during bright moonlit nights and others preferring darker periods. Predator-prey relationships can shift with lunar phase, as moonlight makes it easier for predators to hunt, but also makes it easier for prey to detect approaching threats. Some researchers have found correlations between lunar cycles and ecological processes such as leaf litter decomposition rates or soil respiration, though the mechanisms for such effects, if real, remain unclear. The moon may also affect atmospheric tides, creating subtle periodic variations in atmospheric pressure and winds, though these effects are much smaller than oceanic tides and difficult to measure against the background of weather variations. Throughout human history, different cultures have created myths and stories to explain the moon's features, phases, and movements. Many cultures saw shapes or figures in the pattern of Maria and highlands on the moon's near side. Western tradition speaks of the man in the moon, seeing the dark Maria as forming facial features, while other cultures identified different patterns. Some saw a rabbit or hare in the moon, particularly in East Asian and Central American traditions, while others saw a woman, a toad, or various other figures. These interpretations demonstrate how humans naturally seek patterns and meaning in the objects around us, finding familiar forms even in the random arrangement of lunar geological features. The moon's small size relative to Earth, only about 1/4 of Earth's diameter and 1/80th of Earth's mass, places it among the larger moons in the solar system relative to its planet. Only Charon, Pluto's moon, is larger relative to its primary body. This unusually large moon-to-planet ratio represents part of what makes the moon's giant impact origin hypothesis compelling, as normal planet formation processes tend to produce relatively small moons. The energy involved in the giant impact that formed the moon was sufficient to melt and partially vaporize both Earth and the impactor, creating the most violent event in Earth's history after the planet's initial formation. The fact that Earth survived this catastrophe and eventually cooled to become a habitable world demonstrates the resilience of planetary bodies and the ultimate constructive outcomes that can emerge from apparently destructive events. Looking toward the future, the moon will continue its gradual recession from Earth, though this process will eventually halt as the Earth-Moon system evolves toward a final state where both bodies are tidally locked to each other with the same face of each constantly facing the other. In this configuration, Earth's rotation period would match the Moon's orbital period, which by that time would be much longer than today, perhaps equivalent to about 50 to 60 current days. However, this final state lies billions of years in the future, and other factors will intervene before it arrives. The Sun will eventually begin to expand as it evolves off the main sequence, and within about 5 billion years the Sun's expansion into a red giant will likely engulf both Earth and the Moon, ending their long relationship in a very different way than their tidal evolution would suggest. For now though, and for countless generations to come, the Moon will continue to grace our night sky, waxing and waning in its eternal cycle, pulling on our oceans, stabilising our planet's tilt, and providing a constant reminder of the larger cosmos of which we are a part. The Moon represents both a neighbour we have visited and a frontier for future exploration, both a subject of scientific study and an object of beauty and inspiration. Understanding the Moon through science deepens rather than diminishes its wonder, revealing the intricate processes and vast timescales that shape our corner of the universe. As we drift towards sleep, we can reflect on the fact that the same Moon that lights the night sky tonight has shone down on Earth for more than 4 billion years, witnessing the rise of the oceans, the emergence of life, and the eventual appearance of beings capable of looking up and wondering about its nature. The Moon abides, patient and constant, a silver companion in the darkness, a gentle presence marking the passage of time while inviting contemplation of the deep history written in its ancient cratered face. The next story is about to begin. Please relax and enjoy. The universe is not empty. It might look that way on a clear night when you tilt your head back and see the darkness between stars, but that darkness is not a void. It is furnished. Between the points of light, drifting through the enormous distances that separate one star from another, there are tiny solid particles floating silently in space. These particles are called cosmic dust, and they are real physical material, not a metaphor, not an abstraction, but actual grains of matter, each one smaller than you could see with your naked eye, scattered across the galaxy and beyond. Tonight we are going to walk through 100 small facts about cosmic dust, each one a gentle step into understanding the fine texture of the universe. You do not need to memorize them. You do not need to hold on to them. Just let them pass by like particles drifting through a sunbeam, and if sleep finds you along the way, that is exactly right. Cosmic dust exists across space. It is not confined to one special region or reserved for exotic locations. It floats between stars in our own galaxy, gathers in clouds where new stars will someday form, and drifts in the space between galaxies as well. When astronomers look out at the universe, they are always looking through some amount of dust, even if they cannot see it directly. The dust is there, mingling with the thin gas that fills interstellar space, creating what scientists call the interstellar medium. This medium is not truly empty. It is a mixture, mostly gas with a small fraction of solid dust grains mixed in. The gas is far more abundant by mass, but the dust plays a role that is larger than its small quantity might suggest. Even though dust makes up only about 1% of the mass of the interstellar medium, it has a profound effect on how we see the universe and how stars and planets come to be. Each grain of cosmic dust is extremely small. If you were to hold one in your hand, you would not be able to see it without a microscope. Most dust grains are less than a micrometer across, smaller than a red blood cell, closer in size to the particles in cigarette smoke or fine talcum powder than to grains of beach sand. Some are even smaller, just a few dozen nanometers wide, while others might reach a micrometer or slightly more. They are irregular in shape, not perfect spheres, and their surfaces are rough and varied. Despite being tiny, these grains have power. They can block light, they can scatter it, they can absorb energy from nearby stars and re-radiate it in different forms. A single grain does very little, but when trillions upon trillions of grains gather together in a cloud, they can hide entire regions of a galaxy from view, or glow softly in wavelengths of light that our eyes cannot detect. Cosmic dust is made of mixtures. There is no single recipe that applies everywhere, because dust grains form in different environments and from different materials. Some grains are rich in carbon. These carbonaceous grains might include graphite, similar to the material in a pencil, or more complex carbon compounds. Other grains are made of silicates, minerals that contain silicon and oxygen, often combined with elements like magnesium, iron, or aluminum. These silicate grains are somewhat similar to the minerals found in rocky planets, including Earth. In the coldest parts of space, dust grains can also accumulate icy coatings, thin layers of frozen water, carbon monoxide, carbon dioxide, methane, or ammonia. These ices cling to the grain surface and can change the grain's properties, making it slightly larger and altering how it interacts with light and with other molecules in space. The composition of a dust grain tells a story about where it came from and what it has experienced. Dust is not the same everywhere. Its composition depends on local conditions. In regions where old, cool stars are gently releasing material into space, the dust might be rich in carbon or silicates, depending on the chemistry of the star's outer layers. In areas where massive stars have exploded in the past, the dust might contain heavier elements forged in those explosions. In dense clouds where molecules are forming and ice is accumulating, the grains might be coated and chemically different from grains drifting in the emptier regions between clouds. As dust travels through space, it can be altered by radiation from nearby stars, by shock waves from stellar winds or supernovae, or by collisions with other particles. Over time, a single grain might be processed and reprocessed many times, its surface etched or coated, its structure changed. The universe is not a factory with one assembly line. It is a vast and varied workshop where dust is constantly being made, modified, and recycled. There can be long distances between individual dust grains, especially in the less dense parts of space. If you could shrink yourself down and float between the stars, you might drift for a very long time before encountering a grain. The space between grains is measured in meters, sometimes kilometers, depending on the local density. Yet despite these large gaps, when you consider the enormous volumes involved, cubic light-years of space, the total amount of dust becomes significant. A region might contain only a few grains per cubic meter, but multiply that by the volume of an interstellar cloud, and you have trillions upon trillions of grains contributing to the cloud's overall properties. Dust does not need to be tightly packed to have an effect. It just needs to be present, spread out over vast distances, waiting patiently. In space, dust can drift for ages without being disturbed much at all. There is no wind in the conventional sense, no rain to wash it away, no surface for it to settle on. A dust grain can float along, carried by the faint pressure of starlight or the thin currents of gas flowing through the galaxy, travelling for thousands or millions of years without a significant collision. It is motion at a pace so slow and gentle that it makes a glacier look hurried. The grain is not in a rush. It has nowhere urgent to be. It simply exists, drifting, occasionally interacting with a photon of light or brushing against a gas molecule, but mostly just moving through the silence, a tiny solid island in an ocean of near vacuum. This stillness is part of what makes cosmic dust so calming to think about. It is matter in no hurry, shaping the universe over timescales that dwarf human lifetimes. The motion of dust grains is influenced by forces that are almost imperceptible on human scales, but significant over cosmic time. Radiation pressure, for instance, is the gentle push that light exerts when it strikes a dust grain. Each photon carries a tiny amount of momentum, and when it hits a grain, some of that momentum is transferred. For a single photon hitting a single grain, the effect is negligible. But a dust grain near a bright star is being hit by countless photons every second, and over time, this steady pressure can push the grain outward, away from the star. Small grains are pushed more easily than large ones, because the force depends on the grain's surface area, while resistance to movement depends on its mass. Very small grains can be blown out of star systems entirely by radiation pressure, while larger grains resist this force and remain closer to their parent stars. This sorting by size is one of the ways the universe organizes matter without any conscious intention, just physics acting patiently over time. Dust grains can also be influenced by magnetic fields. The interstellar medium is threaded with weak magnetic fields, invisible but real, extending across vast distances. Some dust grains contain magnetic materials like iron, and these grains can align themselves with the local magnetic field, much like a compass needle aligns with Earth's magnetic field. When grains align, they affect how light passing through the dusty region is polarized. By measuring this polarization, astronomers can map the magnetic fields in molecular clouds and other regions. revealing the invisible structure that shapes the movement and behavior of gas and dust. Magnetic fields can also influence how clouds collapse to form stars, providing support against gravity in some cases and channeling material in specific directions in others. Dust becomes a tool for studying these fields, a visible tracer of invisible forces. Just one more small fact, and then we drift. Sometimes, when astronomers look at images of space, they see dark patches that appear to be holes in the star field. These dark regions look empty, as if there are simply no stars there. But often that darkness is an illusion. The region is not empty. It is filled with dust. Dust clouds can block visible light very effectively, creating dark nebulae that stand out against the brighter background of more distant stars. The dust does not destroy the light. It absorbs it and scatters it. When visible light from a star encounters a dust grain, some of that light is absorbed by the grain, and some is scattered in different directions. If the dust cloud is thick enough, very little visible light makes it through to reach our eyes or our telescopes. The result is a shadow, a dark silhouette where a cloud of dust hangs between us and the stars beyond. These dark regions are not voids, they are veils. One of the most famous dark nebulae is the Coal Sack, visible in the southern hemisphere. It appears as a dark patch in the Milky Way, a region where the brightness of the galactic band is interrupted by what looks like a hole. But the Coal Sack is not a hole. It is a molecular cloud filled with gas and dust, located about 600 light-years from Earth. The cloud blocks the light from the stars behind it, creating the illusion of emptiness. If you could travel to the Coal Sack and look around from inside it, you would see dust and gas, surrounding you, faintly illuminated by the light of distant stars. You would not perceive it as a void. The darkness is purely a matter of perspective, a consequence of standing on the far side and looking through a dusty curtain. Dust can absorb starlight and warm slightly. When a dust grain absorbs a photon of visible or ultraviolet light, that energy is converted into heat. The grain's temperature rises by a tiny amount. Because the grain is solid, it can then re-emit that energy, but not in the same form it received it. Instead of giving off visible light like a hot star would, the dust grain radiates energy at much longer wavelengths, in the infrared part of the spectrum. This re-emission is gentle and quiet. Infrared light is lower in energy than visible light, more like warmth than glare. The grain glows softly in the infrared, invisible to our eyes but detectable by instruments designed to see heat. This process transforms the light of the universe. A bright star might pour out visible and ultraviolet light. But if that light passes through a dusty region, some of it is converted into infrared glow, changing the energy budget of the surrounding space. The temperature of a dust grain depends on its distance from nearby stars and on the intensity of the radiation it receives. Close to a hot, bright star, dust grains can be warmed to several hundred degrees Kelvin, warm enough to glow brightly in the mid-infrared. Farther away, in the cold outer regions of a molecular cloud, dust grains might be only a few tens of degrees above absolute zero, emitting faintly in the far infrared and sub-millimeter wavelengths. The grain does not hold on to heat indefinitely. It radiates energy continuously, finding a balance between the energy it absorbs and the energy it emits. This balance is dynamic and depends on the local environment, making dust a sensitive indicator of conditions in different regions of space. This means that darkness in visible light can hide brightness in infrared. A cloud that looks completely black in an optical photograph might light up beautifully when observed with an infrared telescope. The dust is quietly glowing, warmed by the hidden stars embedded within the cloud or by nearby stars whose light has been absorbed. Astronomers have learned to look at space in multiple wavelengths precisely because dust changes what is visible. A region that seems cold and empty in one kind of light can reveal itself as warm and active in another. The universe has layers of visibility, and dust is one of the things that creates those layers. It is a reminder that seeing is not always straightforward, that what looks dark might only be dark in one narrow slice of the electromagnetic spectrum. Infrared observations have transformed our understanding of star formation. Before infrared telescopes became widely available, astronomers could only study the later stages of starbirth when young stars had cleared away enough of their surrounding dust to be visible in optical light. But the earlier stages, the collapse of a cloud core, the formation of a protostar, the assembly of a protoplanetary disk, all happen hidden inside thick dust envelopes. Infrared light can penetrate these envelopes, allowing astronomers to see what is happening inside. They can watch as material falls onto a growing protostar, observe the structure of the disk where planets will form, and measure the temperature and density of the surrounding gas and dust. Infrared astronomy has opened a window onto processes that were previously invisible, revealing the messy, complex reality of how stars and planets come into being. Dust also filters light by scattering. When starlight passes through a dusty region, blue light is scattered more efficiently than red light. This happens because blue light has a shorter wavelength, and dust grains of certain sizes are particularly good at redirecting short wavelength light in random directions. Red light with its longer wavelength is less affected and passes through more easily. The result is that the starlight emerging from the other side of a dust cloud is redder than it was when it went in. Astronomers call this process interstellar reddening or extinction, though the light is not truly extinct, just filtered and redistributed. The effect is similar to what happens during a sunset on Earth, when the sun's light passes through a long path of atmosphere and dust, scattering away the blue and leaving the reds and oranges to reach our eyes. In space, this reddening is permanent for any observer looking through the dust, giving distant stars a tinted appearance like a cosmic sunset that never ends. The amount of reddening depends on the amount of dust along the line of sight and on the properties of the dust grains themselves. Larger grains scatter light differently than smaller grains, and grains with different compositions have different scattering properties. By carefully measuring the colours of stars and comparing them to what those colours should be based on the star's temperatures and spectral types, astronomers can determine how much reddening has occurred. This, in turn, tells them how much dust lies between Earth and the star. It is a technique that requires precision and care, but it provides valuable information about the distribution of dust in the galaxy and helps correct observations for the effects of extinction. This scattering effect has practical consequences for astronomers. When they measure the brightness and colour of a distant star, they have to account for the dust between here and there. If they do not, they might think the star is cooler and dimmer than it really is, because the dust has made it look redder and has blocked some of its light. By studying the amount of reddening, astronomers can estimate how much dust lies along the line of sight and correct their measurements accordingly. Dust becomes a factor in almost every observation of distant objects. It is a kind of tax that space imposes on light, a subtle alteration that must be accounted for if you want to understand what you're truly seeing. Interstellar extinction varies with wavelength in a predictable way, and astronomers have developed mathematical models called extinction curves to describe this variation. These curves show how much light is absorbed and scattered at different wavelengths, from the ultraviolet through the visible and into the infrared. The shape of the extinction curve depends on the size distribution and composition of the dust grains, and by fitting observed extinction to these models, astronomers can learn about the properties of the dust. For example, a feature in the ultraviolet part of the extinction curve, known as the 20 angstrom bump, is thought to be caused by small carbon-rich grains. The presence and strength of this feature tells astronomers about the abundance and nature of carbonaceous dust in different regions. Dust is one reason the universe can look different depending on the kind of light you use to observe it. In visible wavelengths, dust creates dark lanes and obscures whole sections of galaxies. In infrared, those same regions glow warmly, revealing star formation and hidden stellar populations. In ultraviolet, dust blocks light even more strongly, making regions with heavy dust appear almost completely dark. In radio wavelengths, dust has less effect, and you can often see through it to structures and emissions that are invisible in optical light. Each wavelength is a different window, and dust controls how transparent each window is. Astronomers have to choose their windows carefully, depending on what they want to study, and they often combine observations from multiple wavelengths to build a complete picture. Dust is both an obstacle and an informant. It hides some things, but in hiding them, it also tells us where the hidden things are. The development of the multi-wavelength astronomy has been one of the great advances of modern astrophysics. By observing the same object or region in many different wavelengths, gamma rays, X-rays, ultraviolet, visible, infrared, submillimeter, and radio, astronomers can piece together a comprehensive understanding of what is happening. Each wavelength reveals different physical processes and different components of the system. Dust is often the key to interpreting the differences between wavelengths, because its presence so strongly affects what can be seen. A complete picture of a star-forming region, for example, might include visible images showing the young stars that have emerged, infrared images revealing protostars still embedded in their birth clouds, radio observations mapping the molecular gas, and submillimeter data tracing the coldest dust. Together, these observations tell a story that no single wavelength could tell alone. Just one more small fact and then we drift. The space between stars in a galaxy is called the interstellar medium. It is a mixture of gas and dust, spread out over the vast distances that separate one star from another. The gas is mostly hydrogen, the simplest and most abundant element in the universe, with some helium and trace amounts of heavier elements. The dust is the solid component, the tiny grains we have been describing drifting along with the gas. The interstellar medium is thin, far thinner than any vacuum we can create on Earth, but it is not nothing. It is the fabric from which new stars are made. In certain regions, the interstellar medium becomes denser, gathering into clouds where gravity can begin to pull material together. These clouds are the nurseries of stars, and dust is a crucial part of the process. The interstellar medium is not uniform. It has structure, with regions of different densities, temperatures and compositions. Some regions are diffuse and warm, with gas spread out thinly and dust grains separated by large distances. These regions might have densities of only a few atoms per cubic centimetre and temperatures of thousands of degrees. Other regions are cold and dense, with densities reaching millions or even billions of atoms per cubic centimetre and temperatures just a few degrees above absolute zero. These cold, dense regions are molecular clouds, where gas atoms have come together to form molecules and where dust is abundant. The interstellar medium is constantly changing, stirred by stellar winds, supernova explosions, and the gravity of passing objects. It is a dynamic environment, full of motion and transformation. Dust often gathers in the spiral arms of galaxies. Spiral galaxies, like the Milky Way, have beautiful curved structures that sweep outward from the galactic centre. These spiral arms are not solid structures, they are density waves, regions where stars, gas and dust crowd together more closely than in the spaces between the arms. As gas and dust move through a spiral arm, they are compressed, and this compression can trigger the formation of new stars. Because dust is part of the interstellar medium, it tends to be more concentrated in these arms as well. The spiral arms are where star formation is most active and where dust plays its role most visibly. The spiral structure of galaxies is maintained by gravitational interactions and orbital mechanics. Stars and gas orbit the galactic centre, but not all at the same speed. The differential rotation creates regions where material piles up temporarily, forming the spiral arms. These arms rotate more slowly than the stars themselves, so individual stars and clouds pass through the arms over time. When gas and dust enter a spiral arm, they experience increased density and gravitational forces, which can trigger collapse and star formation. The newly formed stars light up the arm, making it visible and prominent. As these stars age and the gas and dust move on, the arm persists as a wave pattern, continuously fed by new material entering from behind. Dust lanes in spiral galaxies are beautiful dark streaks that trace where dust is thicker. When you look at an edge-on spiral galaxy, you can often see a dark band running along the plane of the galaxy's disk. This band is not empty space, it is dust, concentrated in the thin disk where the galaxy's gas and stars also reside. The dust creates a silhouette, a charcoal-like line that shapes the galaxy's appearance. These dust lanes are a signature feature of spiral galaxies, and they tell astronomers where the raw material for future stars is located. Even in face-on spirals, you can see darker patches and streaks winding along the spiral arms, outlining the structure in shadow. The dust lane in an edge-on galaxy can be remarkably thin compared to the galaxy's overall size. A typical spiral galaxy might be tens of thousands of light years across, but the dust layer might be only a few hundred light years thick. This thin layer marks the mid-plane of the galactic disk, where gravity has pulled the dust and gas into a concentrated sheet. The thinness of the dust layer is maintained by a balance between gravity, which pulls material toward the midplane, and the random motions of gas clouds which cause the layer to puff up slightly. The result is a delicate structure, a flat ribbon of dust threading through the galaxy, visible as a dark line when seen from the side. Our own galaxy, the Milky Way, is a spiral galaxy, and we live inside its dusty disk. When we look up at the night sky, the Milky Way appears as a band of light arcing across the heavens. This band is our view of the galaxy's disk from the inside, looking through the plane where most of the stars, gas and dust reside. In some directions, the band looks dense and bright, crowded with stars. In other directions, there are dark patches and gaps, regions where dust blocks our view of more distant stars. Dust within the galactic plane is one reason the night sky looks richer and more textured in some directions than others. It is also why we cannot see all the way across the galaxy in visible light. There is simply too much dust in the way, absorbing and scattering the light before it reaches us. Our position in the Milky Way's disk gives us a unique but limited perspective. We are located about 26,000 light-years from the galactic centre, in a region known as the Orion Arm, or Orion Spur, a minor spiral arm between two major arms. From this position, looking inward toward the centre of the galaxy, we look through a long path of dust and gas in the galactic plane. Looking outward, away from the centre, we look through less dust, and our view is clearer. This is why the part of the Milky Way visible in the direction of the constellation Sagittarius, toward the galactic centre, appears so dense and dramatic, while the part visible in the opposite direction, toward Auriga and Perseus, is less intense. Dust shapes our view and determines what we can see from our particular vantage point. The galactic centre is an example of a region that is bright in many wavelengths, but difficult to see in visible light from our position. The centre of the Milky Way is located about 26,000 light-years away, in the direction of the constellation Sagittarius. It is a crowded, energetic place, home to millions of stars, clouds of gas and dust, and a supermassive black hole with a mass of about 4 million times that of the Sun. But when we try to observe it in visible light, we see very little. The dust along the line of sight absorbs and scatters most of the visible light before it can reach Earth. To study the galactic centre, astronomers use infrared and radio telescopes, which can see through the dust. In those wavelengths, the centre reveals itself, a bustling hub of activity hidden behind a dusty curtain. The dust does not make the galactic centre disappear, it just makes it invisible in certain kinds of light, reminding us that what we see depends on how we choose to look. Infrared observations of the galactic centre have revealed a complex and dynamic environment. There are dense clusters of stars, some of them orbiting very close to the central black hole. There are massive clouds of gas and dust, some actively forming stars and others being disrupted by intense radiation and winds from nearby massive stars. There are filaments of hot gas, loops of magnetic field, and structures shaped by past explosions and outflows. The galactic centre is not a calm place. It is one of the most energetic and chaotic regions in the Milky Way. But from our perspective, hidden behind dust, it appears almost invisible in visible light. Dust has preserved its secrets for most of human history, only revealing them when we developed the technology to observe in other wavelengths. Just one more small fact, and then we drift. Star-forming regions are places where the interstellar medium has gathered into cold, dense clouds. These molecular clouds are thick with gas and dust, and they are some of the coldest environments in the galaxy, with temperatures often just a few tens of degrees above absolute zero. In these frigid conditions, gravity can begin to pull material together. Over time, clumps within the cloud grow denser, and as they do, they begin to heat up. Eventually, if a clump becomes dense and hot enough at its core, nuclear fusion ignites, and a new star is born. But this process does not happen quickly or easily. It takes time, and it requires help. Dust plays a helpful role in this slow transformation. The journey from cloud to star can take millions of years. It begins with a molecular cloud, a vast region of space filled with gas and dust, often extending for tens or hundreds of light years. Within this cloud, there are variations in density. Some regions are slightly denser than others, perhaps because of turbulence in the gas, or because a passing shock wave from a supernova or stellar wind has compressed the material. These denser regions experience slightly stronger gravity, and they begin to pull in more material from their surroundings. As they grow, their gravity increases, and they pull in material even faster. This is the beginning of gravitational collapse, the process by which a cloud core becomes a protostar. Dust provides surfaces where molecules can form. In the cold environment of a molecular cloud, atoms and simple molecules drift around, occasionally colliding with the dust grain, When they land on the grain surface, they can stick for a while, held by weak forces. While they are stuck, they have time to meet other atoms and molecules that have also landed on the grain. Chemical reactions that would be too slow or unlikely to happen in free space can occur on the grain's surface, where reactants are brought together and held in place. One of the most important reactions is the formation of molecular hydrogen, H2, from individual hydrogen atoms. Molecular hydrogen is the dominant molecule in star-forming clouds, and dust grains act as tiny laboratories where much of this molecule is assembled. Without dust, the chemistry of the interstellar medium would be different, and the process of star formation might be less efficient. The surface of a dust grain is not smooth or uniform. It has defects, irregularities, and active sites where atoms can bind more easily. When a hydrogen atom lands on the grain, it can wander across the surface, hopping from site to site until it encounters another hydrogen atom. When two hydrogen atoms meet, they can bond together to form H2, releasing a small amount of energy in the process. The newly formed molecule then evaporates from the grain's surface and drifts away into the surrounding gas. This process is happening continuously on countless dust grains throughout a molecular cloud, gradually converting atomic hydrogen into molecular hydrogen and building up the molecular content of the cloud. Dust also blocks light, and that blocking is helpful in star-forming clouds. When a cloud is dense and cold, it needs to stay cold in order to collapse under its own gravity. If too much energy enters the cloud from nearby stars, it can heat the gas and create pressure that resists collapse. Dust grains absorb that incoming light, preventing it from heating the gas as much as it otherwise would. The dust then re-radiates the energy as infrared light, which can escape from the cloud more easily. In this way, dust acts as a cooling agent, helping the cloud shed excess energy and maintain the cold, dense conditions needed for gravity to do its work. It is a gentle thermostat, regulating the temperature by transforming high-energy visible and ultraviolet light into low-energy infrared. This cooling process is essential for star formation. Without it, the thermal pressure in the cloud would be too high, and gravity would not be able to overcome it. The cloud would remain stable, neither collapsing nor dispersing, and stars would never form. Dust allows the cloud to cool below the temperature at which thermal pressure balances gravity, tipping the balance in favor of collapse. Once collapse begins, the process accelerates. As the cloud core contracts, it becomes denser and gravity becomes stronger. Material falls inward, heating up as it converts gravitational potential energy into kinetic energy. At the center of the collapsing core, a protostar begins to form, growing as it accretes material from the surrounding cloud. Once a cloud begins to collapse, dust grains begin a new role. They start to collide and stick together. In the densest parts of a collapsing cloud, where a new star is forming, there is often a disk of material orbiting around the young star. This disk is made of gas and dust, and it is the leftover material from the collapse. Within the disk, dust grains move around, occasionally bumping into each other. When they collide, gently they can stick together, held by weak forces like static electricity or van der Waals forces. Each collision that results in sticking makes the grain a little bit larger. Over time, two grains become one slightly bigger grain. That bigger grain can collide with others and grow larger still. This process is slow and delicate. If the collisions are too violent, the grains shatter instead of sticking. But in the right conditions, it works. The sticking process depends on the properties of the grains and on the conditions in the disk. Grains with icy coatings tend to stick together more easily than bare grains, because the ice can act like glue, binding the grains when they touch. Temperature plays a role too. If the disk is too warm, the ice evaporates, and sticking becomes harder. Turbulence in the disk can cause collisions to be too violent, breaking grains apart instead of allowing them to grow. But in the cooler, calmer regions of the disk, the conditions are just right. Grains collide gently, stick, and grow, beginning the long process of building larger bodies. As dust grains stick and grow, they move from the realm of microscopic particles into the realm of pebbles. A pebble, in the context of planet formation, is not necessarily something you could hold in your hand. It might be anywhere from a millimeter to a centimeter or more in size, but it is much larger than the original dust grains. These pebbles are the intermediate stage between dust and planets. They continue to collide and grow, sometimes through gentle sticking, sometimes through gravitational attraction, as they become large enough to pull on each other. Over millions of years, these pebbles can accumulate into larger bodies called planetesimals, which are kilometers across and can have enough gravity to pull in more material actively. Planetesimals collide and merge, forming protoplanets, and eventually, if the conditions are right, a rocky planet like Earth or a core for a giant planet can form. The growth from pebbles to planetesimals is one of the most challenging aspects of planet formation to understand. There is a size range, roughly from centimeters to meters, where objects tend to be fragile and prone to breaking apart when they collide rather than sticking together. This has been called the meter-size barrier, and it presents a puzzle for planetary scientists. How do growing bodies cross this barrier without being destroyed? Several mechanisms have been proposed. One idea is that turbulence in the disk can concentrate pebbles into dense clumps, where their combined gravity is strong enough to hold them together and allow them to collapse into larger objects. Another idea is that some bodies grow more quickly than others, perhaps because they start in a particularly dense region of the disk, and once they reach a certain size, they can accrete material gravitationally without needing to rely on collisional sticking. The details are still being worked out, but the general picture is clear. Somehow, the disk manages to build planetesimals, bridging the gap between tiny grains and kilometer-sized bodies. The peaceful big picture is simple. Worlds begin as dust learning to hold hands. Every rocky planet, every asteroid, every moon orbiting a gas giant started as tiny grains of dust in a disk around a young star. The details of planet formation are complex, with many processes happening at once. Gravitational instabilities, collisions, migration, and interactions with gas. But the fundamental starting point is always the same: dust. Without dust, there would be no solid surfaces to stand on, no cores for planets to build around, no raw material from which rocky worlds could grow. Dust is not just background material. It is the seed from which solid worlds emerge. Protoplanetary disks are beautiful and varied. Observations with powerful telescopes, particularly in the infrared and submillimeter wavelengths where dust emits strongly, have revealed disks around young stars with rings, gaps, spirals, and asymmetries. These features are signatures of planet formation in progress. A gap in a disk, for example, might be carved out by a young planet whose gravity clears a path through the surrounding material. A spiral pattern might be caused by gravitational interactions between the disk and a massive planet, or by instabilities in the disk itself. By studying these structures, astronomers can learn about where planets are forming, how massive they are, and how they interact with the disk. Dust makes these observations possible because it is the dust that emits the infrared and submillimeter light that reveals the disk's structure. Many of the solid materials in rocky planets come from dust that existed long before those planets formed. The elements that make up Earth, the iron in its core, the silicon and oxygen in its rocks, the carbon in living organisms, were not created when Earth formed. They were forged in stars that lived and died billions of years ago. When those stars ended their lives, they released material into space, material that condensed into dust grains and drifted through the galaxy. That dust eventually found its way into a cloud of gas that would collapse to form the Sun and its planets. The dust became part of the disk around the young Sun, and from that disk Earth and the other planets grew. In a very real sense, the ground beneath our feet was once cosmic dust, floating silently between the stars. This connection between stars, dust, and planets is profound. It means that the atoms in our bodies have travelled through space, been part of stars, been expelled into the interstellar medium, condensed into dust, drifted for millions of years, and finally settled into the planets and life forms we see today. We are made of recycled material, stardust, in the most literal sense. This is not a poetic metaphor. It is the result of astrophysical processes that have been operating for billions of years. Every breath you take contains atoms that were once inside a star. Every rock, every drop of water, every living cell carries a history that stretches back to the earliest generations of stars in the universe. Just one more small fact, and then we drift. Dust is a traveller with many quiet origins. Not all dust comes from the same source, and not all dust is the same age. Some dust is freshly made, condensed from material released by stars in the relatively recent past. Other dust is ancient, having drifted through space for billions of years, surviving multiple cycles of cloud formation and starbirth. Understanding where dust comes from requires looking at the life cycles of stars, because stars are the primary factories where the elements that make up dust are created. Stars spend most of their lives fusing hydrogen into helium in their cores. This is a stable phase that can last for millions to billions of years depending on the star's mass. But eventually the hydrogen in the core runs out, and the star must find new sources of fuel. What happens next depends on the star's mass. Low-mass stars like the Sun swell into red giants, expanding and cooling as they begin fusing helium in their cores and hydrogen in a shell around the core. Higher-mass stars go through more stages of fusion, creating heavier elements like carbon, oxygen, neon, and silicon. The details are complex, but the key point is that stars create new elements through nuclear fusion, elements that did not exist in the universe when it first formed. Older stars can shed material into space through gentle outflows. When a star like the Sun nears the end of its life, it swells into a red giant, its outer layers expanding and cooling. These cool, extended atmospheres are places where atoms can come together to form molecules and dust grains. The star's outer layers are not tightly bound. Stellar winds, driven by radiation pressure and pulsations, can carry this material away into space. As the material moves outward and cools, conditions become right for dust to condense. Carbon-rich stars produce carbonaceous dust, while oxygen-rich stars produce silicate grains. These grains, newly formed in the stellar wind, drift away from the dying star and enter the interstellar medium, joining the reservoir of dust that already exists. This process is gentle and gradual, a quiet contribution to the galaxy's dust budget. The amount of dust produced by a single star is small, but there are billions of stars in a galaxy, and many of them will go through this phase. Over millions of years, the cumulative contribution from all these stars is significant. Asymptotic giant branch stars, a specific phase in the evolution of low to intermediate mass stars, are particularly prolific dust producers. They pulsate, creating shocks in their outer atmospheres that help drive material outward, and they have strong stellar winds that carry the dust and gas away from the star. These stars are responsible for much of the dust production in galaxies today. Some dust is also made in more energetic cosmic events, though we can talk about these events calmly. When a massive star reaches the end of its life, it can explode in a supernova, a sudden and powerful release of energy. The explosion ejects the star's outer layers into space at high speeds, and within those ejected layers, elements heavier than hydrogen and helium are scattered. Carbon, oxygen, silicon, iron, and many others. As this material expands and cools, some of it condenses into dust grains. Supernova dust is rich in heavy elements, elements that were created in the star's core through nuclear fusion and during the explosion itself. This dust is dispersed into the interstellar medium, where it mixes with dust from other sources and becomes part of future generations of star-forming clouds. Supernovae are powerful, but the dust they create is part of a long, slow cycle, not an immediate catastrophe. Supernova dust was particularly important in the early universe, when galaxies were young and there were not yet many low-mass stars contributing dust through stellar winds. Massive stars evolve quickly, exploding as supernovae within a few million years of their formation, and they can produce substantial amounts of dust in a single event. This dust helped seed the early galaxies, providing the raw material for the first generations of planet formation and contributing to the opacity that shaped how those galaxies evolved. Observations of distant young galaxies have revealed large amounts of dust, more than can easily be explained by stellar winds alone, suggesting that supernovae played a major role in dust production in the early universe. Dust participates in long cycles, forming, drifting, getting processed by radiation and shocks, joining clouds, and eventually becoming part of new stars and planets again. A dust grain that forms in the wind of a dying star might drift through the galaxy for millions of years before it encounters a molecular cloud. In that cloud, it might be incorporated into a new star-forming region, where it helps cool the gas and provides a surface for chemistry. If it ends up in a disk around a young star, it might stick to other grains and become part of a growing planet. Or it might be destroyed, heated by radiation, shattered by a shock wave from a nearby supernova, or vaporized as it falls into a star. Even when destroyed, the atoms that made up the grain are not lost. They remain in space, available to form new dust later. This recycling is continuous and patient. Nothing is wasted. It just changes shape and location, over and over across billions of years. The timescale of this recycling varies. In the densest parts of the galactic disk, where star formation is active and the interstellar medium is constantly being stirred by stellar winds and supernovae, a dust grain might be cycled through clouds and stars relatively quickly, perhaps on timescales of tens to hundreds of millions of years. In the outer parts of the galaxy, where the density is lower and star formation is less frequent, a grain might drift for billions of years without being incorporated into a new star. Some grains are lucky. They avoid destruction and remain intact for most of the galaxy's history. Others are processed repeatedly, each cycle altering their structure and composition. The idea of recycling is comforting. It means that the universe is not running down in a simple linear way. It is renewing itself constantly. The dust that helps form stars today will someday be part of new dust, and that new dust will help form stars and planets in the future. The cycle connects the past and the future, linking the death of old stars to the birth of new ones. It also connects us to the rest of the cosmos, the atoms in our bodies, the elements in the air we breathe, the materials in the buildings and tools around us. All of these came from dust, and before that, from stars. We are made of recycled stardust, participants in a process that has been going on for billions of years and will continue long after we are gone. Dust also carries information. By studying the composition of dust grains, astronomers can learn about the conditions in which they formed. Grains rich in certain elements suggest they came from specific types of stars. Grains with icy coatings tell us about the cold environments they passed through. Isotopic ratios within grains can reveal details about nuclear processes in stars and supernovae. Some meteorites contain tiny grains that are older than the solar system, pre-solar grains that formed in other stars before our sun existed. These grains are messengers from the distant past, carrying information about the galaxy as it was billions of years ago. By analysing them in the laboratory, scientists can learn about the history of stellar evolution, nucleosynthesis, and the interstellar medium in ways that would be impossible otherwise. Dust is not just material, it is a record, a library written in atoms and minerals. Presolar grains are remarkable. They survived the collapse of the solar nebula and the formation of the solar system, somehow avoiding being vaporized or altered. They were incorporated into meteorites, which drifted through space for billions of years before falling to Earth, where scientists found them and recognized them as something extraordinary. By measuring the isotopic composition of these grains, researchers can determine which type of star they came from and when that star lived. Some grains show isotopic patterns consistent with red giant stars, others with supernovae, and still others with more exotic sources. Each grain is a tiny time capsule, a fragment of a star that existed long before the sun, preserved through billions of years of cosmic history. Just one more small fact and then we drift. Because dust blocks visible light, astronomers often use infrared and radio observations to see through dusty regions. Infrared light has longer wavelengths than visible light, and it is less affected by dust. While visible light might be almost completely absorbed and scattered by a thick dust cloud, infrared light can pass through much more easily. This makes infrared telescopes invaluable for studying star-forming regions, the centers of galaxies, and other areas where dust is abundant. Infrared astronomy is like feeling warmth instead of looking at brightness. It is a quieter kind of seeing, more subtle, but in many cases more informative. The development of infrared astronomy required overcoming significant technical challenges. Earth's atmosphere absorbs much of the infrared light from space, so ground-based infrared telescopes have to be located at high, dry sites where the atmosphere is thinner and contains less water vapor. Even then, many important infrared wavelengths can only be observed from space. Infrared detectors also have to be cooled to very low temperatures to reduce thermal noise, which can overwhelm the faint signals from distant objects. Despite these challenges, infrared astronomy has flourished, with missions like the Infrared Astronomical Satellite, the Spitzer Space Telescope, the Herschel Space Observatory, and the James Webb Space Telescope revealing the universe in unprecedented detail. Infrared telescopes have revealed whole populations of stars that were invisible in optical surveys. Young stars buried deep in molecular clouds, for example, can be detected by their infrared glow even when no visible light escapes. Protostars, still in the process of forming, are often surrounded by thick envelopes of dust that absorb all their visible light and re-emit it in the infrared. By observing in the infrared, astronomers can watch stars being born, tracking their growth and evolution in ways that would be impossible if they relied only on visible light. Infrared. Astronomy has also revealed the structure of dusty disks around stars, showing where planets might be forming and how material is distributed within those disks. It is a powerful tool for studying processes that are hidden by dust. Infrared observations have also transformed our understanding of galaxies. Many galaxies, particularly those undergoing intense star formation, emit most of their energy in the infrared rather than in visible light. This happens because the young, massive stars in these galaxies produce copious amounts of ultraviolet light, which is absorbed by surrounding dust and re-emitted in the infrared. In visible light, these galaxies might appear modest or even faint, but in the infrared they blaze brightly. Infrared surveys have discovered populations of these infrared galaxies, revealing a component of cosmic star formation that was previously hidden. Radio observations are another way to see through dust. Radio waves have even longer wavelengths than infrared, and they are affected by dust even less. Radio telescopes can detect emissions from molecules in dense clouds, trace the motions of gas, and map the magnetic fields that thread through dusty regions. Radio astronomy is particularly useful for studying the coldest and densest parts of molecular clouds, where even infrared light might struggle to penetrate. By combining radio and infrared observations, along with data from other wavelengths, astronomers can build a complete picture of what is happening inside dusty regions, how the gas and dust are distributed, how they are moving, and how they are interacting with each other and with nearby stars. Radio telescopes can also observe the emission from specific molecules, providing detailed information about the chemistry and physical conditions in molecular clouds. Molecules like carbon monoxide emit radio waves at characteristic frequencies, and by measuring the intensity and Doppler shift of these emissions, astronomers can map the distribution and velocity of the gas. This reveals the internal structure of clouds, showing where dense cores are located, how the gas is flowing, and whether there are outflows or jets associated with young stars. Radio observations complement infrared data, providing a different perspective on the same regions and adding to our understanding of the processes at work. Dust also creates some of the most beautiful and informative patterns in astronomy. In images of nebulae and galaxies, dust often appears as dark lanes or bright filaments, depending on whether it is blocking light or glowing with absorbed energy. These patterns outline clouds, trace spiral arms, and mark where future stars may form. Dust is an artist, shaping the visual appearance of the universe in ways that make abstract physics tangible and aesthetically moving. When you look at a photograph of a star-forming region, with its dark cores and glowing edges, you are seeing dust at work, blocking, scattering, absorbing and re-radiating light, all in the service of creating new stars. Some of the most iconic astronomical images feature dust prominently. The Horsehead Nebula, for example, is a dark cloud of dust silhouetted against a bright background nebula. Its shape, resembling the head of a horse, is sculpted by the distribution of dust and gas, carved by the radiation and winds from nearby stars. The pillars of creation in the Eagle Nebula are towering columns of gas and dust, their shapes defined by the erosion caused by intense ultraviolet light from young stars. These pillars are regions where new stars are forming, protected from the surrounding radiation by the dense dust and gas. Dust gives these structures their form, their visibility, and their scientific interest. Dust traces the skeletal structure of the interstellar medium. In maps of galaxies, dust follows the spiral arms, highlighting the regions where the interstellar medium is densest and most active. In maps of molecular clouds, dust shows where the cloud is thickest and where collapse might be beginning. Dust is not just an obstacle to observation, it is an indicator, a signpost that tells astronomers where to look for interesting phenomena. By studying where dust is and how it is distributed, scientists can learn about the large-scale structure of galaxies, the life cycle of the interstellar medium, and the conditions that lead to star formation. Dust is both subject and tool. It is the thing being studied and the means by which other things are studied. Infrared and radio observations have also taught us that dust is dynamic. It is not static scenery. It moves, changes, and responds to its environment. Dust can be pushed by radiation pressure from bright stars, creating bubbles and cavities in the surrounding medium. It can be swept up by stellar winds or supernova shockwaves, compressed into dense filaments where new star formation might be triggered. It can evaporate when exposed to intense ultraviolet light, releasing the atoms and molecules locked in its structure back into the gas. Dust participates actively in the physics of the interstellar medium, shaping and being shaped by the energetic processes happening around it. The interaction between dust and radiation is particularly important in regions near hot, massive stars. These stars emit intense ultraviolet radiation, which can heat and ionize the surrounding gas, creating what is known as an HI region. At the boundary between the ionized gas and the surrounding neutral material, dust is subjected to intense radiation. The dust absorbs the ultraviolet light and heats up, sometimes reaching temperatures of several hundred degrees. This hot dust glows brightly in the infrared, creating a bright rim around the HI region. The radiation pressure can also push the dust outward, creating a shell or bubble that expands into the surrounding medium. Over time, this can clear out a cavity around the star, redistributing the dust and altering the structure of the interstellar medium. Even in a quiet room, far from any telescope or cloud of interstellar gas, you're part of a universe where tiny grains drift, settle, and slowly build complexity over immense time. The same processes that create dust between the stars also created the materials in the world around you. The wood in furniture, the metal in electronics, the silicon in glass. All of these came from elements forged in stars, condensed into dust, and eventually incorporated into the Earth when the solar system formed. Dust connects the grand scale of galaxies to the intimate scale of daily life. It is a reminder that the universe is not something distant and separate. It is the foundation of everything we know, including ourselves. The story of dust is also the story of patience. Nothing in the universe happens quickly by human standards. Dust grains take thousands or millions of years to drift from one place to another. Stars take millions of years to form. Planets take tens of millions of years to grow. The recycling of material through stars, dust, and the interstellar medium takes billions of years. Yet all of these slow processes add up to create the rich and complex universe we see today. Dust teaches us that transformation does not require haste. It requires time, gentle forces, and the accumulation of countless small changes. Cosmic dust can dim starlight, but it also makes new light possible later, by helping shape the places where stars and planets are born. This duality is important. Dust is often thought of as an obstacle, something that gets in the way and makes observations harder. But it is also an enabler. Without dust, molecular clouds would have a harder time cooling and collapsing. Without dust, molecules like H2 might not form efficiently. Without dust, planets might not be able to grow from tiny grains into worlds large enough to hold atmospheres and oceans. Dust is both the veil and the seed, both the shadow and the foundation. It takes light away in one form and gives it back in another. It hides the present and makes the future possible. This is the 100th fact, but it is not the end of the story. The universe has been building with dust for billions of years, and it will continue long after this moment. Stars will keep forming, planets will keep growing, and dust will keep drifting, recycled endlessly through the great cycles of matter and energy. There is no rush, there is no deadline. The universe is patient, and tonight you can be patient too. Let the facts settle in your mind like grains settling in a cloud. Slowly, gently, without force. You do not need to hold on to them. You do not need to understand everything perfectly. The details will still be there tomorrow, waiting quietly in the structure of the cosmos. The universe is not empty. It is full of tiny solid particles floating silently, shaping the darkness and the light, making new worlds possible. And as you lie here, breathing slowly, feeling the weight of your body easing into rest, you are connected to that vastness, made of the same elements, shaped by the same processes, part of the same unbroken chain that leads from dust to stars to planets to this moment, right now where sleep is beginning to arrive on its own. The next story is about to begin. Please relax and enjoy. A comet is a small object moving through our solar system, and at its most basic level, it's made of ice, dust, and rocky material. When you picture what a comet actually is, you might imagine something bright and dramatic streaking across the sky, but the physical object itself, the actual solid part, is often quite modest in size. Scientists sometimes describe comets as dirty snowballs, though this phrase doesn't tell the whole story. Many comets are better thought of as icy, dusty, somewhat fragile rocks. They're not perfectly round balls of clean snow. They're irregular, lumpy ancient objects that have been drifting through space for billions of years, carrying within them a mixture of frozen water, frozen gases, tiny grains of dust and bits of stone. The solid centre of a comet, the part that actually exists as a single piece, is called the nucleus. And when we talk about the nucleus, we're talking about something that might be surprisingly small compared to what you see when a comet becomes visible in the night sky. Many comet nuclei are only a few kilometres across. To give you a sense of scale, that's roughly the size of a small city or a large town. You could walk across the surface of many comet nuclei in an hour or two if you were able to stand on one, though of course you'd be standing on something extremely cold, covered in dark dust and utterly silent in the vacuum of space. For most of its journey through the solar system, a comet looks quite faint. It doesn't announce itself, it doesn't glow on its own. It's simply a small, dark object moving along its orbit, too dim for most telescopes to notice unless someone is specifically looking for it. But something changes when a comet gets closer to the sun. As sunlight begins to warm the surface of the nucleus, something quiet and beautiful begins to happen. The ice on and just below the surface of the comet doesn't melt the way ice melts on Earth. Instead, it sublimates. Sublimation is the process where a solid turns directly into a gas without passing through a liquid phase first. On Earth, you can see this happen with dry ice, which is frozen carbon dioxide. Leave dry ice out on a table and it doesn't form a puddle. It simply releases vapour and disappears. The same thing happens on a comet. The frozen water, frozen carbon dioxide, frozen carbon monoxide and other ices trapped in the nucleus begin to turn into gas when the sun's warmth reaches them. That escaping gas doesn't just vanish into space, it carries something with it. As the gas rises from the surface, it lifts fine dust particles that were mixed in with the ice or resting on the comet's surface. This creates a cloud of gas and dust around the nucleus, and this cloud has a name: the coma. The coma is the fuzzy glowing envelope that surrounds the tiny nucleus, and it can become much, much larger than the nucleus itself. Even if the nucleus is only a few kilometres wide, the coma can swell to become tens of thousands or even hundreds of thousands of kilometres across. Suddenly a small object becomes something vast and diffuse. The coma is what makes comets look like they have a soft glow when you observe them through a telescope, or, if the comet is bright enough, with your own eyes. It's not a sharp, hard object. It's a gentle cloud of particles and molecules illuminated by sunlight, spreading outward in all directions from the hidden nucleus at the centre. The process of creating a coma is gradual and responsive to changing conditions. As the comet continues to approach the sun, the intensity of sunlight increases, and with it, the rate of sublimation. More ice turns to gas, more dust is lifted, and the coma grows larger and brighter. This isn't a violent process, not an explosion or a sudden release. It's more like a slow exhalation, a steady breathing out of material that has been locked in ice for eons. The gas molecules that escape from the nucleus are moving at speeds determined by their temperature, spreading outward in all directions, carrying dust grains along with them. Some of these molecules and dust grains will eventually be pushed away into the comet's tail. Others will simply disperse into space, adding to the thin scattering of matter that exists between the planets. But the coma is not the only feature a comet can develop. Many comets also grow tails, and here's where things become even more interesting. A comet's tail is not necessarily a single structure. Comets can have more than one kind of tail, and each kind forms for a different reason. Many comets develop what's called a dust tail. This tail is made of fine grains of dust that were lifted off the nucleus by the escaping gas. Once these dust particles are free in space, they don't just sit still. They're pushed outward by the gentle but persistent pressure of sunlight. Yes, sunlight has pressure. Photons, the particles of light, carry momentum, and when they strike a dust grain, they give it a tiny push. Over time, those tiny pushes add up, and the dust gets blown away from the comet in a broad, curving tail. The dust tail often looks softer and more diffuse than other structures around the comet, and because the dust particles are heavy enough to be influenced by the comet's own motion through space, the dust tail tends to curve slightly, tracing a gentle arc. The pressure of sunlight is extraordinarily faint by everyday standards. You don't feel sunlight pushing on you when you stand outside on a sunny day because the pressure is so small. But in space, where there's no air resistance and objects can be very light, even this faint pressure can have significant effects over time. Dust grains released from a comet are small and have very little mass, so the accumulated push from millions of photons striking them can gradually alter their trajectory. The smallest, lightest grains are pushed the most, while larger, heavier grains are pushed less. This creates a sorting effect in the dust tail, with different sized particles spreading out along slightly different paths, contributing to the tail's broad, fan-like appearance. Many comets also form an ion tail. An ion is an atom or molecule that has lost or gained electrons, giving it an electric charge. When the sun releases a stream of charged particles, mostly electrons and protons, this stream is called the solar wind. The solar wind rushes outward from the sun in all directions, travelling at speeds of hundreds of kilometers per second, and when it encounters the gas in a comet's coma, it can strip electrons from the gas molecules, turning them into ions. These ions are now electrically charged, and because they're charged, they respond to the magnetic field carried by the solar wind. The solar wind sweeps these ions directly away from the sun in a straight line, creating what's called the ion tail. The ion tail often looks straighter and narrower than the dust tail. It's usually blue or cyan in colour in photographs because the ions often include molecules like carbon monoxide, which glow in specific colours when they're energised by sunlight. The dust tail, by contrast, appears yellowish or white because it's simply reflecting sunlight off tiny particles. The interaction between the solar wind and a comet's ion tail is complex and dynamic. The solar wind carries with it the sun's magnetic field, which is frozen into the flow of charged particles. When this moving magnetic field encounters the ionized gas around a comet, it drapes around the coma and stretches out into a long, narrow tail. The ions are trapped in the magnetic field and carried away at high speed. This process is efficient and fast, which is why the ion tail can extend to enormous lengths, sometimes stretching for tens of millions of kilometers, far longer than the orbit of Mercury. The ion tail is also more responsive to changes in the solar wind than the dust tail. When the sun releases a particularly strong burst of solar wind called a coronal mass ejection, the ion tail can brighten suddenly, twist, or even break off entirely in a disconnection event. Here's something that surprises many people when they first learn about comets. A comet's tails generally point away from the sun, not behind the comet like a trail. If you imagine a comet as a car driving down a road, you might think its tail would stream out behind it the way your hair streams behind you when you ride a bike. But that's not what happens. The tails point away from the sun because they're being pushed by sunlight pressure and by the solar wind, not by the comet's motion through space. This means that as a comet approaches the sun, its tail can actually trail behind it. But as the comet swings around the sun and begins to move away, the tail goes first, pointing outward ahead of the nucleus as the comet retreats back into the cold outer solar system. The comet, in a sense, can move tail first on part of its journey. Sometimes a comet can appear to have multiple streamers or a fan shape, especially if you're looking at it with very sensitive instruments. The structure of a comet's tail can be complex, shaped by the interaction of dust, ions, magnetic fields, and the comet's rotation. Different viewing angles can make the same comet look quite different. If you're viewing a comet from an angle where you're looking along the plane of its orbit, the tail might appear very long and dramatic. If you're viewing it from above or below its orbital plane, the tail might appear shorter or more spread out. The three-dimensional structure of a comet and its tails can be challenging to visualize from a two-dimensional photograph or from our vantage point on Earth. Astronomers sometimes use multiple observations from different locations or times to reconstruct what the comet's tail structure really looks like in space. The nucleus itself is usually too small to see directly, even in powerful telescopes. Most of what we notice when we look at a bright comet is the coma and the tail. The actual icy, rocky body at the heart of it all might be just a few pixels in even the best images, or completely invisible. Yet that tiny nucleus is the source of everything. All the gas, all the dust, all the glowing beauty of a comet comes from this small, fragile object, losing pieces of itself bit by bit as it travels near the sun. Comet tails can change from night to night as the comet rotates, and releases jets of gas and dust from different areas on its surface. If you watch a comet carefully over several nights, you might notice that its tail shifts shape, or that streamers appear and fade. This is the comet responding to the changing angle of sunlight on its rotating surface and to variations in the solar wind. A comet can look dramatic and otherworldly, even though fundamentally it's simply sunlight interacting with dust and gas in the most straightforward physical way. There's something meditative about the way a comet changes over the course of its approach to the sun. It starts as a faint point of light, barely distinguishable from distant stars. Gradually, night after night, it brightens. A fuzzy halo appears around it, the developing coma. Then, if conditions are right, a faint tail begins to emerge, at first just a slight elongation, then growing longer and more distinct. The comet reaches its peak brightness around the time it passes closest to the sun, and then, as it moves away, the process reverses. The tail fades, the coma shrinks, the brightness diminishes, and eventually the comet returns to being just a faint point, then disappears from view entirely. This cycle can take weeks or months depending on the comet's orbit and how close it comes to Earth and the Sun. Watching this slow transformation is like watching a flower bloom and fade, except the timescale is stretched out and the flower is made of ice and dust and is millions of kilometers away. Comets travel on orbits around the Sun just like planets do. They're part of the solar system, bound by the Sun's gravity, moving along paths that are determined by the same laws of motion and gravitation that govern everything from falling apples to orbiting moons. But while planets move on nearly circular orbits, many comet orbits are very stretched out. They're long oval paths called ellipses, and some of these ellipses are so elongated that a comet might spend the vast majority of its time far, far from the Sun, only briefly sweeping close before retreating again. Comets are often grouped into two broad categories based on how long they take to complete one orbit: short-period comets and long-period comets. Short-period comets are those that return to the inner solar system relatively frequently, typically in under about 200 years. These are the comets we can predict. We know when they'll return. We can track them over multiple passages. Long-period comets, on the other hand, can take thousands of years to complete a single orbit. Some of them may take hundreds of thousands of years, or even longer. For these comets, recorded history covers only a tiny fraction of their journey. Some comets may only visit the inner solar system once in all of human history, before leaving again on a path that will take them back to the outer reaches for millennia. The shape of a comet's orbit tells you something about its history. A very elongated orbit suggests that the comet originated far from the Sun and was perturbed inward by some gravitational interaction. A less elongated orbit might indicate that the comet has been nudged by planets over multiple passes, gradually having its orbit altered into something shorter and more circular. The details of orbital mechanics are fascinating in their precision. Once you know a comet's position and velocity at a particular moment, you can calculate where it will be at any point in the future or where it was at any point in the past, limited only by the accuracy of your measurements and the complexity of accounting for all the gravitational influences acting on it. A comet's closest point to the Sun is called perihelion. This is the moment when the comet is most affected by the Sun's heat and gravity. It's at perihelion that a comet usually becomes most active, releasing the most gas and dust, growing its brightest coma and longest tails. The farthest point in a comet's orbit from the Sun is called aphelion. At aphelion, a comet is cold and quiet. If it's far enough out, it might be completely frozen, inactive, indistinguishable from any other small icy body drifting in the dark. Near perihelion, a comet is usually at its brightest because the increased heating makes the sublimation process much more vigorous. More ice turns to gas, more dust gets lifted away, the coma swells larger, and the tails grow longer and more visible. But this also means that every time a comet passes close to the Sun, it loses a little bit of itself. The ice sublimates away and doesn't come back. The dust drifts off into space. Slowly, orbit by orbit, a comet sheds mass. The amount of material a comet loses during each passage can vary greatly. A very active comet might lose millions of tons of material. A less active comet might lose much less. Over many orbits, this loss adds up. Eventually, a comet can lose so much mass that it becomes much less active, or it can even run out of volatile material entirely. Some comets have been observed to fade over multiple returns, becoming progressively dimmer and less active as their supply of ice diminishes. The surface of a comet can also change in ways that affect its activity. As ice sublimates, non-volatile materials, dust and rocky particles, can accumulate on the surface, forming a crust that insulates the ice beneath. This crust can slow down or even halt sublimation from some areas, reducing the comet's overall activity. However, fresh ice can be exposed through impacts, through thermal stress cracking the crust, or through the collapse of surface features, leading to renewed activity. Comets can be nudged over time by the gravity of planets, especially Jupiter. Jupiter is by far the most massive planet in our solar system, and its gravitational influence is strong. When a comet passes near Jupiter, even if it doesn't come particularly close, Jupiter's gravity can tug on the comet and change its orbit. A comet that was on a long period orbit might get pulled into a shorter orbit. A comet that was already on a short orbit might get thrown onto a different path entirely, or even ejected from the solar system altogether. This gravitational sculpting has been happening for billions of years. Jupiter has likely altered the orbits of countless comets, sometimes capturing them into orbits that bring them near the Sun more frequently, sometimes scattering them outward. Because of this, the orbits of comets are not static. They evolve, over time, shaped by the push and pull of the Sun and the planets. The gravitational influence of planets on comets is an example of what's called the three-body problem in physics. When you have two objects, say the Sun and a comet, calculating their mutual gravitational interaction and predicting their future positions is straightforward. But when you add a third body, say Jupiter, the problem becomes much more complex. In most cases, there's no simple formula that gives you the answer. You have to use numerical methods, calculating the forces step by step through time. This is why predicting the exact behaviour of comets over very long timescales can be challenging. Small uncertainties in the initial conditions or in the positions of the planets can grow over time, making long-term predictions less reliable. The concept of chaos in physics often comes up in discussions of comet orbits. Chaos, in the scientific sense, doesn't mean randomness or disorder. It means that a system is extremely sensitive to initial conditions. A tiny change in the starting position or velocity of a comet can lead to vastly different outcomes over millions of years. This doesn't mean we can't predict anything about comets, but it does mean that there are limits to how far into the future or the past we can accurately trace their orbits. For short-period comets observed over a few orbits, predictions can be very accurate. For long-period comets, or for trying to trace a comet's path millions of years back, uncertainty grows. Many short-period comets are linked to a region of the solar system called the Kuiper Belt, which lies beyond Neptune. The Kuiper Belt is a region filled with icy bodies and small worlds, remnants from the early solar system that never gathered together to form a planet. It's a vast, cold place where objects can be made mostly of ice and rock, preserved in the deep freeze of the outer solar system for billions of years. Some of these Kuiper Belt objects get nudged by gravitational interactions or collisions and fall inward toward the Sun, becoming the short-period comets we observe. The Kuiper Belt is home to many fascinating objects, including dwarf planets like Pluto, Eris, Makemake, and Haumea. These are worlds in their own right, but they share the same icy composition as comets, differing mainly in size. But there's another source of comets, one that's even more distant and more mysterious. Some comets are thought to come from a region called the Oort cloud. The Oort cloud is a hypothesized vast, distant shell of icy objects that surrounds the solar system at an enormous distance. If the Oort cloud exists as scientists believe, it would be far, far beyond the Kuiper Belt, so far that it would take light from the Sun many hours or even days to reach its outer edges. The Kuiper Belt extends from about 30 astronomical units from the Sun to perhaps 50 or 60. An astronomical unit is the average distance from the Earth to the Sun, about 150 million kilometres. The Oort cloud, by contrast, is thought to extend from perhaps 2,000 astronomical units out to as far as 100,000 astronomical units or more. At those distances, the Sun would appear as just a bright star, not the blazing disk we see from Earth. The Oort cloud hasn't been directly observed because the objects in it are too small and too far away to see, even with our best telescopes, but we infer its existence from the comets we do see. Long-period comets come from all directions in the sky, not just from the plane where the planets orbit. This suggests that there's a roughly spherical cloud of icy objects surrounding the Sun at a great distance, and occasionally something disturbs one of those objects and sends it falling inward. What could disturb an object that far out? Passing stars, for one. Even though space is vast and mostly empty, stars do pass relatively close to the Sun from time to time over millions of years. A star passing within a few light years of our solar system could gravitationally nudge objects in the Oort cloud, changing their orbits just enough to send them drifting inward. The gentle pull of the galaxy itself, the tidal forces from the combined mass of all the stars in the Milky Way, can also disturb faraway icy bodies over very long timescales. The idea of the Oort cloud came from the work of Dutch astronomer Jan Oort in the 1950s. He studied the orbits of long-period comets and noticed that many of them seemed to have their aphelia, their farthest points from the Sun, at similar, very large distances. This suggested that there was a reservoir of comets at that distance, and that comets entering the inner solar system for the first time were being perturbed from this reservoir. The Oort cloud is thought to contain billions or even trillions of icy objects, though most of them are quite small. The total mass of the Oort cloud is uncertain, but might be only a few times the mass of Earth, spread out over an enormous volume of space. So a comet, in a sense, can be like a message from the solar system's outermost edges. It spent billions of years in the cold and dark untouched, and then some subtle gravitational nudge set it on a path that would eventually bring it close to the Sun and into view of observers on Earth. Comets may preserve very old material from the early solar system. When the solar system was forming, about 4.5 billion years ago, there was a disk of gas and dust surrounding the young Sun. Planets formed from this disk, growing larger and larger as they swept up material. But not everything got incorporated into planets. In the outer parts of the solar system, where it was cold enough for water and other compounds to freeze, there were countless small icy bodies. Some of these became moons, some clustered in the Kuiper belt, and some were flung outward to form the Oort cloud. Because these objects formed so far from the Sun and have remained cold ever since, they haven't been significantly altered by heat or chemical reactions. They're like time capsules. Studying comets helps scientists learn what the solar system was like long ago, what materials were present in the early disk, what chemical processes were happening, and how planets like Earth eventually came to have water and organic molecules. The early solar system was a chaotic place. The disk of gas and dust that surrounded the young Sun was turbulent, with materials spiralling inward, colliding, sticking together, and sometimes being thrown outward. Temperature varied with distance from the Sun. Close to the Sun, it was hot enough that only rocky and metallic materials could condense into solid particles. Farther out, beyond what's called the frost line or snow line, it was cold enough for water ice to form. This is why the inner planets, Mercury, Venus, Earth, and Mars, are rocky, while the outer planets, Jupiter, Saturn, Uranus, and Neptune, are gas and ice giants. The frost line was a crucial boundary in the forming solar system, and comets originated beyond it, in the cold regions where ice was stable. When spacecraft have visited comets and analysed their composition, they've found a remarkable variety of materials. Comets contain not just water ice, but also frozen carbon dioxide, carbon monoxide, methane, ammonia, and many other compounds. They contain complex organic molecules, the building blocks of chemistry that can lead to life. None of this means comets themselves are alive or that life came from comets in some direct way, but it does mean that comets carried raw ingredients that might have been delivered to the early Earth through impacts, contributing to the mix of chemicals that eventually led to the emergence of life. It's a humbling thought. The water in Earth's oceans, the carbon in your body, might have ridden through space on countless small comets and icy asteroids that crashed into our planet billions of years ago. Earth's water is something of a mystery. Our planet is rocky and formed relatively close to the Sun, yet it has vast oceans. Where did all that water come from? One possibility is that it was delivered by comets and asteroids after Earth had mostly formed. During a period called the Late Heavy Bombardment, roughly 4 billion years ago, the inner solar system experienced an intense period of impacts. Comets and asteroids from the outer solar system rained down on the inner planets. Some of these impacts would have brought water and organic molecules to Earth. How much of Earth's water came from comets versus asteroids is still debated. Studies of the isotopic composition of water in comets, specifically the ratio of deuterium, a heavy form of hydrogen, to normal hydrogen, have shown that some comets have water with a different isotopic signature than Earth's oceans. This suggests that while comets might have contributed some of Earth's water, much of it may have come from asteroids which have water that more closely matches Earth's. A comet nucleus is typically very dark because the dust on its surface absorbs most of the light that hits it. When scientists finally got close-up images of comet nuclei from space missions, one of the surprising discoveries was just how black they are. Many comet nuclei have very low reflectivity, much darker than you might expect for something made mostly of ice. Why is this? The surface of a comet gets coated with a layer of dark dust as ice sublimates away. Ice is bright and reflective, but dust, especially carbon-rich dust, is dark. Over time, as a comet makes repeated passes near the Sun, the surface ice sublimates and escapes, but the dust is often too heavy to be lifted away by the gentle flow of gas. It accumulates, forming a crust. This crust can insulate the ice beneath, making the sublimation process more complex. Gas has to work its way up through cracks and vents in the crust. This is why comets can have jets, streams of gas and dust escaping from active spots where the crust is thinner or broken. The dark surface of comets surprised early researchers who expected to see bright, icy surfaces. The reflectivity, or albedo, of many comet nuclei is only a few percent, meaning they reflect only a tiny fraction of the sunlight that hits them. This is comparable to the reflectivity of asphalt or charcoal. The darkness comes from organic compounds, carbon-rich materials that formed in the early solar system, mixed with silicate dust. These materials have been processed by radiation over billions of years, further darkening them. The dark surface also means that comets can heat up more than you might expect when they're near the Sun, because dark materials absorb heat more efficiently than bright ones. Jets can make a comet's brightness flicker and shift over the course of hours or days. As a comet rotates, different areas of its surface are exposed to sunlight at different times. An area that was in shadow and inactive might rotate into sunlight and suddenly begin releasing gas and dust, creating a new jet. An area that was active might rotate into shadow and go quiet. This rotation, combined with the irregular shape of many comet nuclei, means that the activity of a comet is rarely uniform or steady. It pulses and shifts in a complex dance of light, shadow, rotation, and sublimation. Some comet nuclei are very irregular and lumpy rather than round. They can look like potatoes or dumbbells or jagged rocks. Some comets are actually two or more pieces loosely bound together by their own faint gravity, tumbling through space as a fragile pair or cluster. Comet 67P Churyumov-Gerasimenko, visited by the Rosetta spacecraft, has a distinctive two-lobed shape that makes it look like a rubber duck. This shape might have resulted from two separate objects gently colliding and sticking together, or from uneven erosion over time. The rotation of comets can be complex. Some comets tumble, rotating around multiple axes at once. Others have relatively simple rotation, spinning around a single axis like a top. The rotation can change over time due to the uneven forces from jets pushing on different parts of the surface. This is called non-gravitational acceleration, and it can cause a comet's rotation to speed up, slow down, or change its orientation. Understanding a comet's rotation is important for predicting its behavior and for planning spacecraft missions because the activity and hazards around a comet depend on which areas are active and when. Comets can crack, fragment, or break apart, especially after repeated trips near the Sun. The heating and cooling cycle, the stress of rotation, the loss of mass, all of this can weaken a comet's structure. Sometimes a comet will simply split into two or more pieces, which then travel along slightly different orbits. When a comet loses enough material over many orbits, it can fade into a quieter object over time, no longer producing a visible coma or tail, eventually becoming what's called a dormant or extinct comet, or even just a rocky asteroid-like body that no longer shows any sign of ice. Some asteroids in the inner solar system might actually be the rocky remains of ancient comets that have completely lost their volatile materials. Distinguishing between a true asteroid and an extinct comet can be difficult without detailed analysis of the object's composition and orbit. A comet's life is often a slow process of change, shedding, and return. Each passage near the Sun erodes it a little more. Each orbit brings it back, a little smaller, a little less active. For some comets, this cycle can continue for thousands of years. For others, the end comes more quickly. They break apart, or they're perturbed onto a collision course with the Sun or a planet, or they're ejected from the solar system entirely by a close encounter with Jupiter. There's a kind of gentle tragedy in the life of a comet. It's beautiful because it's dying, slowly giving itself away to space with each close approach to the Sun. But there's also a kind of patience to it. A comet doesn't rush. It follows its orbit year after year, century after century, pulled by gravity along a path it cannot deviate from except by chance encounters. It's a traveller that keeps returning, as long as it lasts. One of the most famous returning comets is Halley's Comet, which completes an orbit roughly every 75 to 76 years. This means that Halley's Comet appears in the inner solar system about once per human lifetime, making it possible for someone to see it twice if they live long enough and are lucky with timing. Halley's Comet has been recorded by observers for centuries, with documented sightings going back over 2,000 years. Ancient Chinese astronomers recorded it. European monks noted it in medieval chronicles. Artists in the Renaissance included it in paintings. The comet appeared in 1066, the year of the Norman conquest, and was later depicted in the Bayeux Tapestry. It returned in 1301, and the Italian painter Giotto may have used it as the model for the Star of Bethlehem in one of his frescoes. It came back in 1456, in 1531, in 1607, in 1682, in 1758, in 1835, in 1910, and most recently in 1986. Each return is an opportunity for a new generation to see the same object their ancestors saw, moving along the same ancient path. The predictability of Halley's Comet was a significant achievement in the history of astronomy. When Edmund Halley calculated its orbit and predicted its return in 1758, he was demonstrating that comets obeyed the same natural laws as planets. They weren't supernatural or divine signs. They were physical objects moving through space according to the laws of gravity and motion. This was part of a broader shift in human understanding during the scientific revolution, when natural phenomena that had once been attributed to gods or magic were explained through physics and mathematics. Halley himself didn't live to see the comet's return. He died in 1742, but his prediction was vindicated, and the comet was named in his honour. A bright comet can become part of art and history simply because people notice it together. It's a shared experience, something unusual in the sky that everyone can see, something that doesn't fit the normal pattern of stars and planets. In eras before artificial light drowned out the night sky, a bright comet would have been unmistakable, a glowing visitor that grew night by night, its tail stretching across the heavens. People tried to interpret comets as omens or signs. They didn't know what comets were, but they knew they were something different, something that came and went according to no calendar they understood. Ancient sky watchers often kept careful records of comets' positions, their brightness, the length and direction of their tails. These records, preserved in old manuscripts and inscribed on stone, are valuable to modern astronomers. By comparing ancient observations with current knowledge of comet orbits, scientists can sometimes identify which historical apparition corresponds to which known comet, tracing its path back through history. Chinese astronomical records are particularly valuable for this kind of historical research. Chinese astronomers kept detailed records of celestial events for thousands of years, including comets, novae, and other phenomena. These records are sometimes more complete and systematic than European records from the same periods. By analysing these old observations, astronomers can verify the orbits of known comets, discover previously unknown periodic comets, and study how comet activity has changed over time. Comets helped early astronomers realise the sky is not perfectly unchanging. For a long time, influenced by ancient Greek philosophy, many scholars believed the heavens were eternal and immutable, that only the Earth experienced change and decay. Comets challenged this view. Here were objects that appeared, changed, and disappeared. They moved against the background of stars. In the 16th century, the astronomer Tycho Brahe carefully measured the position of a bright comet and determined that it must be farther away than the Moon. This was significant because it meant that change was happening in the celestial realm, not just in the earthly one. Later, Edmund Halley used Isaac Newton's newly developed laws of motion and gravitation to calculate the orbits of comets recorded in historical records, and realised that the comets of 1531, 1607 and 1682 were actually the same object returning on a roughly 76-year cycle. He predicted it would return in 1758. Halley didn't live to see it, but the comet did return as predicted, and it was named in his honour. This was powerful evidence that comets were natural objects following predictable laws, not supernatural omens. Tycho Brahe's measurements were revolutionary because they used parallax, the apparent shift in position of an object when viewed from different locations. Tycho measured the comet's position from his observatory and compared notes with other astronomers across Europe. If the comet had been close to Earth, below the Moon, its position against the background stars would have shifted noticeably when viewed from different places. But Tycho found no such shift, meaning the comet was much farther away, out among the planets. This shattered the old Aristotelian belief that comets were atmospheric phenomena, weather in the upper air rather than celestial objects. Not every comet becomes bright and famous. Many are only visible with telescopes, faint smudges of light that never develop prominent tails or large comas. Some comets are discovered and catalogued and never seen again because their orbits take them back out into the distant solar system for thousands of years. Comets are often given designations that include letters and numbers. A comet discovered before it's confirmed to be periodic might be designated with C, followed by the year, and a code indicating when in that year it was found. If the comet is confirmed to orbit the Sun with a period of less than 200 years, it's given a P designation, and a number, like P1 for Halley's Comet, the first periodic comet recognised. Comets can also be named after their discoverers, sometimes with multiple names if multiple people independently found the same comet. In the modern era, many comets are discovered by automated sky surveys that scan the sky night after night, looking for anything that moves or changes. These surveys have names like Pan-STARRS, Linear or SOHO, and comets found by them often carry those names. The naming conventions for comets have evolved over time. In the past, comets were often named after the person or people who discovered them, sometimes leading to comets with multiple names if several observers found it independently. Now the naming is more systematic. The designation tells you about the comet's type and when it was discovered, and the name typically acknowledges the discoverer or the survey that found it. For example, comet C2020F3, Neowise, was a comet discovered in 2020 during the first half of March, designated by the letter F, was the third comet discovered in that period, hence the number 3, and was found by the Neowise Space Telescope. A comet's brightness depends on many factors: the size of its nucleus, how active it is, how close it comes to the Sun, how close it comes to Earth, and the angle at which we view it. Even a relatively small comet can look grand if it happens to pass close to Earth and develops a large coma and long tail. Conversely, a large comet that stays far from both the Sun and Earth might remain faint and unimpressive. Predicting how bright a comet will become is notoriously difficult because it depends on how much gas and dust the comet will release, and that can vary unpredictably. Some comets have been expected to put on spectacular shows and then fizzled, releasing less material than predicted. Others have surprised astronomers by becoming brighter than expected. Comets are individuals. Each one has its own composition, its own structure, its own history of heating and cooling, and these differences mean that each comet behaves a little differently when it approaches the Sun. Comet Eson in 2013 was a good example of a comet that didn't live up to expectations. Early predictions suggested it might become extremely bright, perhaps even visible during daytime. But as it approached the Sun, it became clear that it wasn't releasing as much material as hoped, and then, as it passed very close to the Sun, it disintegrated entirely. What had been anticipated as the comet of the century ended up being a disappointment for many observers, though scientifically it was still valuable to watch a comet break apart under extreme conditions. Conversely, Comet Hale-Bopp in the late 1990s exceeded expectations, becoming one of the brightest and most widely observed comets of the 20th century, visible to the naked eye for many months. The unpredictability of comets is part of their charm and part of the challenge for astronomers. Unlike planets, whose positions can be predicted with extraordinary precision centuries in advance, comets can surprise you. They can brighten suddenly, or fade, or split apart. Each comet is a unique object with its own behaviour, and part of the excitement of comet astronomy is that you never know quite what you're going to get. As comets travel along their orbits, they can leave behind trails of dust. This dust doesn't disappear. It continues to orbit the Sun along a path similar to the comet's orbit, spreading out over time into a long stream that follows the comet's path like a river of invisible particles. When Earth, in its own orbit around the Sun, crosses one of those dust streams, something beautiful happens. We get a meteor shower. A meteor is what you see when a tiny grain of dust or a small pebble enters Earth's atmosphere at high speed and burns up due to friction with the air. The grain itself is often smaller than a grain of sand, but it's moving so fast, tens of kilometers per second, that when it hits the atmosphere, it heats the air around it to thousands of degrees. The air glows, and we see a brief streak of light across the sky. A shooting star, though it's not a star at all, just a bit of comet dust meeting its end in a brilliant flash. The speed at which meteor particles hit Earth's atmosphere depends on several factors, including the relative velocity of Earth and the dust stream. Earth orbits the Sun at about 30 kilometers per second. If a dust particle is also orbiting the Sun in the same direction as Earth, but at a different speed, the collision speed is the difference between the two velocities. If the particle is moving opposite to Earth's motion, the speeds add together, leading to much higher impact velocities. This is why some meteor showers produce faster meteors than others. The Leonids, for example, are known for producing very fast meteors because Earth runs almost head-on into the dust stream from Comet Tempel-Tuttle. Many meteor showers happen around the same time each year because Earth meets the same dust stream again and again as it orbits the Sun. The geometry is predictable. Earth crosses a particular point in its orbit on the same date each year, and if there's a stream of comet dust at that point, we'll see meteors. The Perseid meteor shower, one of the most reliable and popular meteor showers, happens every August when Earth crosses the orbit of Comet Swift-Tuttle. The dust left behind by Swift-Tuttle over many orbits creates a stream, and when Earth plows through that stream, we see dozens of meteors per hour radiating from the constellation Perseus. The Leonid meteor shower in November is linked to Comet Tempel-Tuttle. The Geminids in December are linked to an object called 3200 Phaethon, which might be an extinct comet or a rock-comet hybrid. Each shower is a gentle reminder that space is not empty. It contains small drifting particles, the remnants of comets that passed by long ago. The Geminids are particularly interesting because their source, 3200 Phaethon, doesn't behave quite like a typical comet. It's classified as an asteroid, but it has an orbit that brings it very close to the Sun, and it shows some faint activity that might be the release of the dust. Some researchers think Phaethon might be a rock comet, an object that once had ice but has lost most or all of it, leaving behind a rocky remnant that still releases a little dust when heated. This blurs the line between asteroids and comets, suggesting that these categories aren't as distinct as we once thought. Most comet dust grains are very small, often the size of sand or smaller. A grain of rice would be considered large. Yet these tiny particles moving at cosmic speeds create visible streaks of light when they encounter our atmosphere. The bright streak you see is mostly the air itself glowing from heat, not the grain on fire. The dust grain heats the air in front of it, compressing and ionizing it, and that hot glowing air is what you see as the meteor trail. Often the dust grain itself vaporizes completely in a fraction of a second, never reaching the ground. Only larger pieces, small rocks or bits of metal can survive the journey through the atmosphere and land as meteorites. The vast majority of meteors from comet dust streams burn up entirely, adding a tiny bit of vaporized material to Earth's upper atmosphere. Over the course of a year, Earth sweeps up thousands of tons of cosmic dust, most of it from comets. It settles slowly through the atmosphere, eventually making its way to the ground as fine particles mixed into the air and soil. You've probably breathed in a few atoms that were once part of a comet. This constant influx of cosmic dust is one of the ways Earth continues to gain mass, even billions of years after it formed. The amount is tiny compared to Earth's total mass, but it's a steady drizzle of material from space. Scientists collect cosmic dust from high-altitude aircraft, from ice cores in Antarctica, and from the deep ocean floor. Studying this dust gives insights into the composition of comets and asteroids, and into the history of the solar system. A meteor shower is like Earth passing through a quiet, invisible sprinkle of comet dust. The meteors seem to radiate from a single point in the sky, called the radiant, but this is an effect of perspective. The dust grains are all travelling along parallel paths, but because of the way we view them from Earth's surface, they appear to diverge from a point, much the way parallel railroad tracks seem to converge at a distant point. If you were to trace back the paths of all the meteors in a shower, they'd point back to the same spot in the sky. That spot is named after the constellation it's in, which is why we have the Perseids from Perseus, the Leonids from Leo, the Geminids from Gemini, and so on. Watching a meteor shower is a peaceful experience. You lie on your back, look up at the sky, and wait. Every few minutes, a streak of light flashes across your field of view. Each streak is a fragment of a comet, a tiny traveller ending its journey. It's a connection across time and space. You're seeing the last moment of something that might have been orbiting the sun for thousands or millions of years. The best meteor showers can produce dozens or even over 100 meteors per hour under ideal conditions, though you need dark skies away from city lights to see the fainter ones. The experience of watching a meteor shower is different from looking at planets or stars through a telescope. There's no instrument between you and the sky. You're just there, under the stars, part of the turning Earth as it moves through space, and the meteors are a direct, visceral reminder that you're on a planet moving through a solar system that's full of debris from ancient comets. Spacecraft have flown past comets to take close images and measurements, and each mission has revealed new details about these ancient objects. The Giotto mission, launched by the European Space Agency, visited Halley's Comet in 1986 during its most recent return. Giotto flew within about 600 kilometers of the nucleus, close enough to take detailed images and measurements, even as it was battered by dust particles. The images from Giotto showed that Halley's nucleus was shaped like a lumpy peanut, dark and cratered, with bright jets of gas and dust erupting from specific areas on the sunlit side. It was the first time humanity had seen the nucleus of a comet up close, and it was both familiar and alien, a small, battered rock in space, yet also the source of the beautiful coma and tail that had been observed for millennia. Giotto's encounter with Halley's Comet was hazardous. The spacecraft was travelling at about 70 kilometers per second relative to the comet, and at that speed, even a tiny dust grain hits with enormous energy. Giotto's camera was damaged by a dust impact during closest approach, causing the images to go dark for a moment before the spacecraft recovered. Despite this, Giotto survived and was later retargeted to fly by another comet, Griggs-Yellerup, in 1992. The fact that spacecraft can survive close encounters with comets at all is a testament to careful engineering and some good fortune. NASA's Stardust mission, launched in 1999, flew by Comet Wild 2 in 2004. Stardust had a special purpose. It carried a collector filled with aerogel, a lightweight, porous material that could capture dust particles without destroying them. As Stardust flew through the coma of Wild 2, tiny dust grains embedded themselves in the aerogel. The spacecraft then returned to Earth in 2006, bringing back the first samples of comet material ever collected and returned. Scientists studying those samples found a surprising mix of materials. Some of the dust grains were made of minerals that form at high temperatures, suggesting they had been forged near the sun and then somehow transported out to the cold regions where comets form. This hinted at a solar system that was much more dynamic and mixed in its early days than previously thought. Comets, it seemed, were not just pristine lumps of outer solar system ice, but rather mixtures of materials from all over the early solar nebula. Aerogel is a remarkable material, sometimes called frozen smoke, because it's mostly air but solid. It's the best substance known for gently catching fast-moving particles without vaporizing them. When a dust grain hits aerogel at high speed, it burrows into the material, creating a carrot-shaped track. Scientists can then carefully extract the grain from the end of the track and analyze it with powerful microscopes and spectrometers. The Stardust samples revealed organic molecules, tiny crystals of various minerals, and complex structures that showed these dust grains had been through a variety of processes. The Deep Impact mission, launched in 2005, took a more dramatic approach. It sent a small impactor crashing into Comet Tempel 1 at high speed, while a nearby spacecraft observed. The idea was to excavate material from below the surface crust and see what was inside. The impact created a bright flash and threw up a plume of dust and gas. Observing the composition of that plume gave scientists insights into the interior of the comet, which turned out to be very fine, fluffy material, almost powder-like rather than solid ice. This suggested that comet nuclei are not dense, hard objects, but rather loosely packed aggregates of ice and dust, more fragile than expected. The impact on Tempel 1 was carefully planned and observed by telescopes on Earth and in space, as well as by the Deep Impact spacecraft itself. The bright flash and plume were visible to ground-based observatories, and data from multiple instruments gave a detailed picture of what was thrown out. The material was rich in fine dust and water vapour, and the comet's interior appeared to be much less dense than solid ice, suggesting a porous, fragile structure. Some scientists describe comet nuclei as more like icy dirt piles than solid rocks. The European Space Agency's Rosetta mission, launched in 2004, was perhaps the most ambitious comet mission to date. Rosetta didn't just fly past a comet, it orbited one. In 2014, after a 10-year journey through the solar system, Rosetta arrived at Comet 67P Churyumov-Gerasimenko, a comet with a strange two-lobed shape that made it look like a rubber duck. Rosetta spent over 2 years orbiting 67P, watching it transform as it approached the Sun, observing jets turn on and off, mapping its surface in detail and analysing the gases in its coma. Rosetta also deployed a small lander called Philae, which attempted to land on the surface of the comet. The landing was only partially successful. Philae bounced and ended up in a shadowed spot where its solar panels couldn't get enough light. But it still managed to take images and measurements from the surface before its batteries ran out. Philae sent back the first ever photographs taken from the surface of a comet, showing a landscape of boulders, cliffs, and dust under a pitch-black sky. Rosetta's 2-year observation of 67P was unprecedented. The spacecraft watched the comet wake up as it approached the Sun, with activity increasing month by month. Jets would appear and change, sometimes lasting for hours or days, sometimes appearing and disappearing within minutes. Rosetta mapped the entire surface of the comet in high resolution, identifying different terrain types, smooth plains, rough rocky areas, pits and cliffs. The data from Rosetta filled in countless details about how comets work, how their surfaces evolve, how ice and dust interact, and how the solar wind affects the coma and tail. Philae's landing was a dramatic moment. The lander was released from Rosetta and descended slowly toward the surface, but the harpoons designed to anchor it didn't fire properly, and Philae bounced. It touched down, bounced, touched down again, bounced higher, and finally settled in a location that wasn't the planned landing site. The spot was shadowed, so Philae's solar panels didn't get enough sunlight to keep it powered after its primary batteries ran out. But during the hours it was active, Philae sent back images and data, including measurements of the surface material, which turned out to be much harder than expected, almost like ice covered by a layer of dust. Visiting comets helps scientists study their chemistry and structure directly. Missions have shown that comet surfaces can be surprisingly complex and varied, with cliffs, pits, layered terrain, and smooth plains. Some areas are covered in dust, others show exposed ice. The surface can change rapidly as the comet heats up, with new pits opening and cliffs collapsing. Comets contain molecules that include carbon-based compounds, some of them quite complex. Rosetta detected glycine, an amino acid, in the coma of 67P. Amino acids are the building blocks of proteins, essential to life as we know it. Finding them in a comet reinforces the idea that the chemistry of life might be widespread in the universe, that the raw ingredients were being delivered to young planets throughout the solar system's history. Each comet studied up close adds a new piece to the story of our solar system's origins, revealing a little more about the conditions and processes that led to the formation of planets, moons, and eventually life on Earth. The detection of complex organic molecules in comets has profound implications. It suggests that the building blocks of life aren't rare or special, that they form naturally in space under a wide range of conditions. Comets delivered these molecules to the early Earth, and perhaps to other planets as well. While we don't know exactly how life began on Earth, we do know that the raw materials were present early on, and some of them likely came from comets. Comets glow mainly because sunlight reflects off dust and interacts with gas in the coma. The dust scatters sunlight the way dust in Earth's atmosphere scatters sunlight, giving the coma a soft, diffuse glow. The gas in the coma can also fluoresce. Fluorescence is a process where molecules absorb ultraviolet light from the sun and then re-emit that energy as visible light. Different molecules fluoresce at different colours, which is why some parts of a comet's coma or tail can appear greenish, bluish, or reddish in colour photographs. The greenish glow often comes from diatomic carbon or cyanogen molecules. The bluish ion tail comes from ionized carbon monoxide. These colours are usually faint and hard to see with the naked eye, but cameras and spectrographs can capture them, revealing the chemical fingerprints of the gases in the coma. Spectroscopy is one of the most powerful tools in astronomy. By spreading light out into its component colours or wavelengths, scientists can identify which molecules and atoms are present in a comet's coma. Each type of atom or molecule absorbs and emits light at specific wavelengths, creating a unique pattern like a fingerprint. By comparing the observed spectrum of a comet to known spectra of different substances, astronomers can determine what the comet is made of, even from millions of kilometers away. The solar wind can cause the ion tail to ripple and shift quickly. The solar wind is not perfectly steady. It fluctuates with changes in the sun's activity, with gusts and lulls. When a gust of solar wind hits a comet, the ion tail can respond almost immediately, bending or even disconnecting. Sometimes a comet's ion tail can experience what's called a tail disconnection event, where the entire tail appears to break away from the comet and drift off into space while a new tail begins to form. This is often linked to changes in the solar wind's magnetic field. The magnetic field carried by the solar wind can reconnect in complex ways with the magnetic field around the comet's coma, and this reconnection can sever the tail. It looks dramatic in time-lapse images. The comet's tail just detaches and floats away, leaving the comet briefly tailless before activity builds a new one. It's a reminder that comets are not isolated objects. They're constantly interacting with the solar wind, with sunlight, with the magnetic environment of the sun. Tail disconnection events are more common than you might think. They've been observed in many comets, and they provide a visible demonstration of the invisible processes happening around comets. The solar wind is a plasma, hot, ionized gas, and it carries the sun's magnetic field with it. When this field encounters the magnetized plasma in a comet's ion tail, complex magnetic reconnection can occur, similar to what happens in Earth's magnetosphere during magnetic storms. These events are a reminder that space is full of dynamic, changing conditions. Some comets come very close to the sun, and these are called sun-grazing comets. Sun-grazing comets have orbits that bring them extremely close to the sun's surface, sometimes within a solar radius or less. At such close distances, the heating is intense. The comet can suddenly brighten, releasing enormous amounts of gas and dust in a very short time. Many sun-grazing comets don't survive. They break apart under the stress of the heat and tidal forces from the sun's gravity, or they simply evaporate completely, their material dispersed into the solar wind. Some sun-grazing comets are discovered only hours before they plunge into the sun, detected by solar-observing spacecraft that watch the sun's outer atmosphere. These spacecraft have discovered thousands of small comets over the years, most of them sun-grazing comets that appeared briefly and then vanished. The SOHO spacecraft, the Solar and Heliospheric Observatory, has been particularly prolific at discovering sun-grazing comets. Its coronagraph, which blocks the bright disk of the sun to reveal the fainter corona, has spotted thousands of tiny comets plunging toward the sun. Most of these comets are members of what's called the Kreutz group, a family of comets thought to be fragments of a much larger comet that broke apart centuries or millennia ago. Each fragment follows a similar orbit, all of them sun-grazing, and they occasionally appear as they make their final, fatal dive toward the sun. Gravity shapes comet paths, but there are also tiny non-gravitational forces that can affect a comet's orbit. When a comet releases jets of gas, those jets act like little rocket engines. If the jets are not perfectly symmetrical, if they're stronger on one side of the comet than the other, they can give the comet a small push. This push is tiny compared to the pull of the sun's gravity, but over many orbits it can add up. Those tiny pushes can slightly alter a comet's orbit over time, making its return a little earlier or a little later than gravitational calculations alone would predict. Astronomers have to account for these non-gravitational forces when they try to predict exactly when a comet will appear. It's a humbling reminder that even in the precise science of celestial mechanics, comets retain a bit of unpredictability. The rocket effect from jets is called the Yarkovsky effect, or, more specifically for rotating comets, the Yorp effect, Yarkovsky-O'Keefe-Radzievsky-Paddock effect. These effects can not only change a comet's orbit, but also its rotation rate and the orientation of its spin axis. Over thousands of orbits, these tiny forces can have large, cumulative effects, and they're one reason why predicting the long-term behavior of comets is so challenging. Comets remind us that the solar system is dynamic, not frozen in place. Things move, things change, things collide and break apart. The solar system today is not the same as it was a billion years ago, and it won't be the same a billion years from now. Comets are part of that ongoing story of change. Many comets are discovered by automated sky surveys that scan the sky quietly every night, taking image after image, comparing them to previous images to find anything that has moved or changed. These surveys have names like the Catalina Sky Survey, Pan-STARRS, and the Atlas Project. They use relatively small telescopes and sensitive cameras to cover large areas of the sky. Most of the comets discovered today are found by these surveys, not by amateur astronomers peering through eyepieces. Though amateur discoveries still happen from time to time, the surveys generate enormous amounts of data which are processed by computers looking for moving objects. When a new comet is found, its position is measured, and those measurements are sent to the Minor Planet Center, an organization that tracks small solar system bodies. Over time, as more observations come in, astronomers can calculate the comet's orbit and predict where it will go next. The automation of comet discovery has dramatically increased the number of known comets. Decades ago, discovering a comet was a major achievement for an amateur astronomer. Now, automated surveys discover dozens of comets each year, many of them faint objects that would never have been noticed by visual observers. This has been good for science, providing a much more complete census of the comet population, but it has also changed the culture of comet hunting. The romance of patient hours at the telescope, sweeping the sky for a new fuzzy visitor, has largely been replaced by algorithms processing images from robotic telescopes. A comet can be both ordinary physics and still feel deeply magical to watch. There's no contradiction between understanding how something works and being moved by its beauty. Knowing that a comet's tail is just dust and gas pushed by sunlight doesn't make the sight of a bright comet hanging in the twilight sky any less wonderful. If anything, understanding makes it more wonderful, because you realize the scale and the patience involved. You're seeing an object that might be billions of years old, that has traveled distances that are hard to imagine, that is slowly giving itself away to the void, and that will continue on its path long after you're gone. Watching a comet is a way of touching deep time, of connecting to processes that operate on timescales far beyond human lifetimes. There's something humbling about looking at a comet and knowing that it existed long before humans did, that it will continue to exist long after our civilization is gone. Comets move on. Timescales that dwarf human concerns. They don't care about politics, economics, or history. They simply follow their orbits, governed by gravity and momentum, patient travelers on ancient paths. Watching a comet can put your own life in perspective, reminding you that you're a small part of a much larger, much older universe. A comet is mostly harmless distance and time, not a threat, just a traveller. There are sensational stories about comets crashing into planets, and it's true that impacts have happened and will happen again. But the solar system is vast, and the chances of any given comet hitting Earth are extremely small. The last major impact from a comet or asteroid was the event that helped end the age of the dinosaurs 66 million years ago, and events on that scale are rare. Modern sky surveys are designed in part to find and track objects that might pose a risk, and so far none of the known comets are on a collision course with Earth. Most comets pass by at safe distances, visible only as points of light or faint smudges in telescopes, no danger to anyone. The light you see from a comet is sunlight that has taken a small detour through dust and gas. Photons from the sun travel outward in all directions. Some of them strike a comet, bounce off a dust grain, and travel in a new direction, toward Earth. By the time that photon reaches your eye, it might have travelled for 8 minutes from the sun to the comet, and then however long from the comet to Earth. The journey is straightforward, governed by the physics of light and matter, but the result is something beautiful. Seeing a comet is like witnessing the solar system's outer storage briefly drift past our neighbourhood. Most of the icy material in the solar system is stored far away, in the Kuiper belt and the Oort cloud, cold and invisible. Every so often, a piece of that distant storage comes close enough to warm up and become visible, offering a glimpse of what's out there in the dark. The same gravity that holds your feet to Earth also guides comets on their long arcs through space. It's the universal force, the attraction between masses, operating on every scale from the pull between atoms to the pull between galaxies. A comet orbiting the Sun is following the same fundamental law that makes an apple fall from a tree or the Moon orbit Earth. The equation is simple. The force is proportional to the masses involved and inversely proportional to the square of the distance between them. Yet from that simple equation comes the endlessly varied dance of planets, moons, asteroids and comets, each following its own path, each influenced by the gravitational tugs of everything else. A comet's orbit is a solution to that equation, a trajectory through space that balances speed and distance and the pull of the Sun. Every comet orbit is a quiet example of patience. The comet waits in the cold for years, decades, centuries, millennia. Then it falls inward, briefly warming, briefly shining, and then it retreats again. The cycle repeats as long as the comet lasts. There's no hurry, no urgency. The comet doesn't know it's being watched. It doesn't care. It simply follows the path that physics dictates. Yet to us, observing from our brief human timescale, a comet's return can feel like a reunion with an old distant traveller. We mark its appearances. We note them in records. We tell stories about them. We name them after people who found them or studied them. We send spacecraft to visit them. We try to understand them. And all the while, the comet continues on, indifferent, patient, following its orbit. Comets show how something small can create something vast. The nucleus might be only a few kilometres across, yet the coma can swell to hundreds of thousands of kilometres. The tail can stretch for millions of kilometres, sometimes longer than the distance from the Earth to the Sun. A tiny object through the simple process of sublimation and the interaction. With sunlight and the solar wind can create a structure larger than planets. It's a reminder that size and impact are not always directly related. A small thing, under the right conditions, can become something grand and visible and important. Many of the atoms in comet ice are as old as the early solar system. When the solar system formed from a collapsing cloud of gas and dust, the atoms that would eventually become the Sun, the planets, and the comets were all mixed together in that cloud. The hydrogen in comet ice might have been forged in the Big Bang, the birth of the universe itself, 13.8 billion years ago. The oxygen might have been made inside a massive star that exploded as a supernova billions of years ago, scattering its elements into space where they would eventually become part of the cloud that formed our solar system. The carbon, the nitrogen, the metals, all of them have their own ancient histories. A comet is a collection of ancient atoms that have been on a long journey through time and space, and now they're here, drifting past our planet, briefly visible before moving on. The atoms in your body have similar histories. The carbon in your cells was made in stars. The oxygen you breathe was forged in stellar furnaces. The iron in your blood was created in supernova explosions. You and comets are made of the same stuff, shaped by the same processes, part of the same cosmic story. Comets are messengers carrying information about where we came from, what we're made of, and how the universe works. They're small, cold, fragile objects, but they connect us to the deepest questions about existence and origins. The universe doesn't rush its stories. It tells them in slow cycles, in orbits that take thousands of years, in processes that unfold over billions of years. Stars form, shine for millions or billions of years, and die. Galaxies collide over hundreds of millions of years. Planets migrate, moons form and are destroyed. Comets fall inward and are lost. Everything happens in its own time, according to the laws of physics, without haste, without concern for observers. We, with our short lives and quick thoughts, are just brief witnesses to these long, slow processes. A comet passing by is a chance to touch that deep time, to see something that connects us to the distant past and the distant future. It's a humbling and comforting thought. We're part of something much larger and older than ourselves. Tonight you don't need to chase thoughts about comets or orbits or physics. Let them pass like distant comets themselves, bright for a moment, interesting and beautiful, and then gone. You don't need to hold on to any of this. The knowledge is there if you want it, but right now you can just rest. The comets will continue their journeys whether you think about them or not. The universe will keep unfolding its slow stories. The stars will keep shining, the earth will keep turning, and you can let all of that be, without needing to understand it, without needing to remember it. Just breathe slowly. Feel the weight of your body against the surface beneath you. Notice the quiet. Notice the stillness. You're safe here. You're part of the same universe as the comets, made of the same atoms, following the same laws, and right now your only task is to rest. As you breathe slowly, you can rest inside the same gentle rhythm that guides comets through space. It's steady, quiet, and always moving forward, but there's no urgency. Each breath is like a small orbit, a cycle that completes and begins again. In and out, rise and fall, movement and stillness. The comet doesn't worry about its path. It doesn't wonder if it's going the right way. It simply moves, pulled by gravity, shaped by the physics of the universe, patient and persistent. You can be like that too. You don't need to plan or solve or remember. You can just be, just breathe, just rest. The next breath will come on its own. The next thought will pass on its own. Everything will continue in its own rhythm, and you can trust that. You can let go. Just one more small breath, slow and easy, and then we drift. The comets are out there, moving through the cold and the dark, silent and patient. Some are approaching the sun, warming and brightening. Some are retreating, cooling and fading. Some are far away, barely moving at all against the backdrop of stars. They'll all keep going, each on its own path, each following its own time, and you can rest here, knowing that everything is where it needs to be, including you. The universe is vast, and it's been here for billions of years, and it will be here for billions more. Tonight, in this small moment, you can simply rest within it. You're safe. You're held by the same gravity that guides planets and comets. You're part of the same story, the same slow unfolding, and right now, the only thing you need to do is breathe and rest and drift. Just one more small breath, and then we drift. The next story is about to begin. Please relax and enjoy.